Hello everyone, today we are going over some Leetcode in C++, and today we will be focusing on maximum subarray. So before we get started, we are just going to stick with our usual formulation. Over here, input, we always need to ask ourselves 4 questions. What data structure / algorithm / technique we're going to use. What to do with the data, and then our output. Okay, so to look over the question, given an integer array nums, find the subarray with the largest sum and return its sum. So here what we are doing, according to the problem as stated for the input and output relationship, is that we will be scanning our entire array and try to find the maximum sum within a subarray to be able to start this. And I'm going to introduce you folks to an algorithm that is actually pretty handy in this case, called Kth's algorithm in particular. And in such algorithm, in Kth's algorithm, we really are just scanning throughout the rest of the subarray to find the maximum sum accordingly, depending on various combinations. And it's a pretty efficient algorithm to be able to solve such a problem at the same time. And so what I will be doing in this case is introduce you folks to a new type of algorithm called Kth's algorithm. And in this one, what we will be doing is that we are going to have a series of steps that will actually help us find our particular subarray. So Kth's algorithm, the input that we have is a given array, and what we need to do is return the maximum sum of a subarray. What are we going to do with the data? We are going to find we're going to scan through the array to find the maximum sum of a subarray. We should be able to create a subarray while we're scanning through our given array. Right here. An array to start with. We're going to use Kth's algorithm, and we're going to scan through the array and create a subarray to find the maximum sum of the subarray. Ultimately, to find the maximum sum is what we are returning. So to be able to start, we are first going to initialize a current max number, and then we're going to initialize a global max number, which should be an index of the array, index of the given array. Should be the initial. So that it's much like in the case of having a variable and setting it to 0. Okay, so to be able to start, and current max is going to be equal to nums of 0, as we were already given a vector at the top, and then we're also going to have a global max as well, nums of 0. And then what we will be doing is that we are going to be scanning through array, so we're going to have a for loop, int I is going to be equal to, and the way we construct this for loop is that it's going to be set at the first index, not at the, index at 1, not 0, to be able to start, because we are focusing on a subarray, and a subarray needs to have at least 2 indices inside of it, which is why we can start with 1. So now size I++ as a standard for loop. It's just that a subarray needs to have 2 indices to start, which is why we start with 1. And then what we're going to do is that we're going to set a read declaration of current max, and we're going to use this max type of method from the STL library for setting up our max current max nums. Okay, So what we are doing is that within the subarray that we are figuring out in particular what our max is going to be for every single index of I, and then adding up our current max, which will then be redeclared while we are going through inside this for loop, and then adding on an additional nums as well, ultimately to find a said max. And there will be a series of comparisons while we are going up the for loop to compare exactly what our current max is going to be. And then once we have figured out what our current max is, we will then ultimately set our current max after its redeclaration to a global max, which will then be global max current max, and ultimately we will be returning our global max. Right here. So what we do is set a relation of current max to global max while we are going through the for loop. And so what will happen is that we will be making a series of comparisons throughout the rest of our Kth algorithm to then be able to return the global max as well. And just to be able to clarify on this whole aspect, the reason why we do this is because the space complexity is pretty efficient. It's linear for Kth algorithm, and the space and the time complexity is going to be O of n, where n refers to the size in a constant space for an array. So the more numbers that are available in said array, the longer the program is going to take in constant time, which is a pretty good time complexity to begin. So let's run this up. I need to also, don't forget the semicolons, and also make sure you name everything accordingly. Yep. Okay. There we go, and it's pretty efficient to start with. Again, keeping everything in context, the time complexity for the following solution is going to be O of n, since it's revolving around the size. N represents the size of our given array, and it's going to vary based on time in constant space. And then space complexity is going to be linear of O of 1, because we are not necessarily storing any type of data structure, and we're using really just variables to start with. And so it's also relative to the size of the input, where somewhere in the retrospective constant, but really, since we're not using a data structure, the space complexity is going to be O of 1. So yeah, thank you again for taking time to be able to watch over this. If you found this helpful, feel free to like and subscribe. And if you have any questions, feel free to put them in the comment section as well. And as always, take care. Cheers. Bye. Hello everyone. Today we are going to go over maximum product subarray today in C++. And focusing overall on the line 75. So before we get started, I am just going to create our formulated questions that we need to ask ourselves. We have the input, what data structure / algorithm / technique we're going to use, what are we going to do with the data, and then what is our output. So to answer the questions, given an integer array of nums, find a subarray that has the largest product and return the product. The test cases are generated so that the answer will fit a 32-bit integer. So we have an input that we have given array, and the technique I will explain later over what we are going to do, because both the technique and what we're going to do with the data are pretty standard, hand in hand. And then our output is going to be the maximum product of the subarray. So overall, what we will be doing in terms of this entire problem, but prior to just looking at the input and output, the input that we have is an array of nums to start with, and the output is 6. The reason being is because after scanning every single possible subarray to start with, the 2 and 3 happen to be the highest relative to 3 and 2, and then -2 and 4 to start when comparing all the rest of the numbers all together. And then we can also have an edge case at the same time as well. So given that we have -2 and -1, the result cannot be 2 because -2 and -1 is not a subarray, so they all have to be connected one way or another. So we know the relationship as a result from coming from set examples. And the technique that we are going to focus on is not going to be a data structure to start with. It's going to be focusing on the STL library in C++, so we're going to do a swap and max technique, where these methods are from the STL library, where we're able to swap some of the variables that we're going to initialize first. Then we are going to loop through our array. So what we are going to do is that we will initialize our min, max, and answer relative to the index of the array, given array. And while we are scanning through the array, we have to take in mind of some edge cases, because as highlighted in the example, we will have negative numbers to start with. And the constraints, given the fact that nums of I will range from -10 all the way to 10, consider negative numbers. That is why we're going to use the swap, but really our main technique is going to be the max to begin. Edge case of negative numbers. And then what we are going to do is also max and min makes for duration and swap for edge case. Okay, so overall the technique that we're going to actually focus on is focusing on redeclaration from the STL library. We're going to redeclare our initialized variables first for both the max and the min as they are going through the rest of the array, because we have to consider all other possibilities when we are scanning through the array. And we will redeclare the min and max products accordingly, and the product means to multiply. Alright, so now just be able to go through the rest over what we have done. Okay, so for step 1, in terms of a product, we're going to initialize, and that is 1, 2, 2A, 2B, 2C. Just some following notes that we already have over here to start with, just be able to state everything. So first we're going to declare our max product answer nums 0, that's the first index of our given array. And then what we're going to do, we're going to do the same thing for the max and the min. Max product, min product. The reason why we initialize it this way is because we have to have our given array relative to the number of indices at the same time. And now we're going to start scanning. And typically for arrays, we're going to go with a for loop. But the way we declare our for loop is going to be starting at 1, because 1, a subarray is going to need at least 2 indices to begin with. So we have to start at least at 1 to start with, to be able to get all the elements needed for our subarrays whenever we are scanning. Okay, and then what we're going to do, we're going to take into consideration of some edge cases. And so we have to take into consideration of the possibility of one of the indices being negative, because it's one of our constraints over here. So nums of I, if nums of I is less than 0, then what we're going to do is that we're going to call upon a swap between the current, between the min max product and then the min product accordingly, because we have to take into consideration of all possible negative numbers at the same time, and this would actually shift over, because if we have a -6 for instance and -3 and we don't have the swap, it's going to take into consideration, it won't take into consideration that -6 is going to be less than -3, which is why we perform this at the same time. And then what we're going to do, we're going to do a re-declaration, and what we will do is that we're going to redeclare our min product. It's going to be min of nums of I relative to the min product times nums of I. We're comparing these two ultimately to decide exactly what's going to be the minimum, and then we will also do the same thing for our maximum, for our max product as listed above over here. Max nums, max product. And then finally what we were going to do for our for loop is that we will then have our max product answer, which would then be just the max of both the answer and then the max product ultimately. So we have to decide in particular, make a comparison throughout the rest of the array that we are scanning through, if the max product answer is higher than our given max product, because if it's not, then it's going to go back inside of the for loop and then make some further comparisons and redeclarations between our min and max product as well, ultimately to decide, okay, this is what our maximum product is going to be, and then finally we can return our max product answer. Just want to make sure I got everything already set up in place. Okay, both the test cases already pass. We'll submit, and here we go. So overall, just to give a rundown on how the whole, how our solution works, is that our solution runs in constant time, given the fact that 1, we have an array, and n represents the size of the array, and given the fact it's constant, the time complexity of our given solution is going to be with respect to the size of array. So the longer the array, the longer time it's going to take for our solution. And then in terms of space complexity, given the fact that 1, we aren't calling upon any data structure to be able to actually use or store anything whatsoever. So our space complexity is going to be linear, O of 1. And this is a pretty optimal solution at the same time. And yeah, thanks again. This was Max Product Subarray. If you have any questions or any comments below, feel free to put them in the comment section. And if you like this as well, feel free to like and subscribe. And as always, take care. Cheers. Thank you. Hello everyone. Today we are going to go over some Blind 75 C++, and apologies if I'm not on Leetcode right now. Leetcode is just currently down as of the moment, and just what I'm currently doing is just doing everything local for the most part. And if you are also interested at the same time in knowing how to do this locally, just in case you have a better IDE and understanding with the interface and get the foundation, which is something I highly recommend in this, what you can do is just copy and paste your solution over here. And then since you have your parameters already set in place with string, s, and k, for example, for our following problem up here, what you're going to have to do is first create an instance of solution that can be called right over here. Then you set up your parameters of k and your string, the other string, and then you have k. And then you are going to be returning exactly what they are ultimately asking for. And then I'm going to break down the question over what we need pretty soon. So they will call upon sol solution, character replacement is the method, character replacement is the method, your parameter s which is string, k, and k as well, and then you output your result over here and return 0 as inside your main. But this is just where we will be writing our solution to start. So To be able to go over the question of longest repeating character replacement, you are given a string s and an integer of k. Now, before we do anything else, I'm just going to have our 4 questions, our input, what data structure / algorithm / technique we're going to use, what to do with the data, and then what our output is going to be. I'll just put down output. And I just put return -1 as just sort of a placeholder so the IDE doesn't suddenly freak out. And yes, you can do this in Xcode as well. It's pretty good. And just have the option for C++. So anyway, we have our given input, which is a string and integer k. And I'm just going to put in the rest of the comments over here to start. Just gets further out. Alright, you're given a string s and integer k. You can choose any character of the string and change this into other uppercase English character. You can perform this operation at most k times. Return the length of the longest substring container, the same letter you can get after performing the above operations. Okay, so just to give a breakdown of what we're doing, so it looks like that will be returning the length of the longest substring containing the same letter you can get after performing the above operations. Now, same amount. So, in particular, by what they mean to be able to start is that we just need to return the maximum length of the substring that can be performed by replacing as many most characters. So, going over example 1, we have a given input of string AB, and k of 2. Now, and then the output of this is 4, and the reason being, as they state, is replace the 2 A's with 2 B's and vice versa, as in how many times can you replace the number of characters inside of our given string. And in this case, for example, AA, BA, BBA, it's asking us to replace one of the characters, and in this output it said we can replace it 4 times, such as replace the 1A in the middle of B and form AA, B, 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 A with the longest substring of being B, 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 B with the longest repeating character. So after we replace the character, we would have to see what the longest substring would be after we replace, for instance, 2 characters, and then we could have the longest output accordingly as a result from replacing the 2 characters. Okay, so so K represents the number of characters we can replace, and then we are, again, returning the length of the longest substring containing the same letter you can perform. This was confusing, I apologize, in the output, so it looks like they're returning the length of the longest substring after replacing the k number of characters. Okay, right over here. And the technique that we would do for strings in C++, in this case, for this one, would be the sliding window technique, where it's unlike binary search and then 2-pointer, you are, where binary search is more of a divide and conquer, and you have 3 different variables of a middle, low, and high end. And in 2-pointers, you just have, literally, as the name implies, 2 pointers, your left and your right parts, and this would be helpful for substrings. But in this case, for sliding window, we have 3 variables, which are 2 pointers and 1 max length, where the max length will change. And then with our sliding window, we can use any data structure we want. In this case, we're going to use an array to keep track of all the characters visited in the string to start. So, and then what we'll be doing with our following solution is that we will adjust the window to maximize the length of our substring with the most repeating characters after replacing k number of characters. in our string. We change the size of the array depending on if there are repeated characters. Meaning, if there are repeating characters, we continue. If not, we stop the size of the array. Alright, just to go further in depth of what we need to do with the following data, just given the steps. Alright. 1. We will initialize our 2 pointers and max length. We will initialize an array to keep track of the frequency of characters in the substring which are repeating. And then what we will do is that we are going to loop through the data and expand upon the relationships of our 3 pointers, but starting with the right pointer and our length of string. Then what we will do is then increment the frequency of the right character while going up the string, because if we look at our given array, the rightmost, we are still going up on the right side. Then what we will do is we will update the max frequency in the current substring by creating a function to get the count of our max frequency. Then if the length of the current substring minus the maximum frequency exceeds k, decrement the frequency of the character at the left pointer and move the left pointer as we are moving up our array. And then we will update the max length, not the frequency. We first just to be able to clarify in step 5 is that when we mean by our max frequency, we also mean our array, which represents the frequency. And for step 7, we will update the maximum length of the substring and checking the difference using max from the STL library to compare the max length and characters of the 2 pointers. And then finally what we're going to be outputting over here is going to be returning the max length of the substring, which can be formed by replacing most characters. Alright, now just to be able to give a rundown on what we have done for our input, we're given a string and an integer, and k represents the number of characters we can replace. What data structure / algorithm / technique we're going to use. We're going to use a sliding window technique. We have 3 variables, 2 pointers, and 1 max length. The max length will change, and we will use an array to keep track of all the strings called max frequency. And the steps we will do is that we will initialize a 2 pointer and max length. We will initialize an array to keep track of the frequency of the characters in the substring which are repeating. Then loop through the array and expand upon the relationships of our 3 pointers, but starting with the right pointer and our length of string. Increment the frequency of the right character while going up the string because moving the array to the right side, and then we're going to update our max frequency of our array. Max frequency of our array in the current substring by creating a function to get the count of our max frequency, which is also our array. Then, if the length of the current substring minus the maximum frequency exceeds k, decrement the frequency of the character at the left pointer and move the left pointer as we are moving up the array. And we will update the maximum length of the substring and check in the difference using max from the STL library to compare the max length of characters at the 2 pointers. So now just giving a breakdown, and then ultimately we're just returning the max length. That's just pretty much just want to make sure the notes are all clear. Alright, so now just to be able to go forward, so we're going to have our right side, which is going to be our count, and left side would be that, and then int max length. We're going to be 0, and then we're going to have our array, which is our max frequency. And since one of the constraints, luckily, is the 26 characters, 6 characters of the alphabet, so which should be a vector times int of frequency, which is also called upon from the STL library of 0/26, or no, 26 to 0. There we go, and then we already know. Apologies on that. Alright. Then now we're gonna put in a while loop. We are on step 3 right now. While the right is less than s dot length as indicated by the string, and then increment the right side. We will increment the array with our right pointer, so that means frequency, which is our array, is going to be incremented with our right. Yep, that's right. And then we're going to update our max frequency and max frequency with our array. Get max frequency. We're going to create a function for this. So what we're doing is that this is how we are going to create a subfunction over here. Vector int and frequency over here. Max freq is going to be initialized up here, and for int count frequency max freq equal max freq count. Return max frequency over here. So this is how we will be updating our frequency of our given count that we would have. Make sure you spell everything correctly. Okay, there we go. Going back in a while loop after we just created that function. Now we are going to check the length of the current substring minus the max frequency if it exceeds k, because we can only change one of the characters k number of times. We can change only a certain amount of characters k number of times. Minus left plus 1 minus the max frequency, which that should represent the length within our given array that we are also incrementing at the same time. And then if it's less than a left minus a dot left would also increase. We would then move our following sliding window up our given array from the left pointer, and therefore it would actually be decremented because we've already kept track of it by using the right. As if, imagine we're starting from the beginning, like this is the right immediately, then we keep going, and then we can actually change one of the characters accordingly. So we can change this one and then that one as well as we're moving up, and we are expanding set window, because expanding the window is starting from the right all the way to the left. Alright. After we have done that, we will update the max length as well. Max length, max, by making a comparison between plus 1 as it's moving up the array, and then we're going to increment right as we're expanding the entire window altogether. Alright, that should be good. And then finally what we will be doing is that we will be returning our max length. We just kept the -1 as sort of a placeholder right over here. In the worst case scenario, it would actually return 0 because we've already decided that, oh yeah, it's not really there to start. So to test this out in our given example, I have already AAB, ABBA with our k of 1, and we are supposed to have an expected output of 4 to start. And I'm just going to make sure this is all right, so I'm just going to press play. The result is 4. There we go. Okay, as highlighted by the example up here. Oh wait, this is 2. Oh wait, hang on. Yes, right here, this example over here, that makes sense. AABBA, it was example 2, and the output is 4. Now let's do the same thing if we were to have 2. And then have the same string from example 1. Supposed to have an expected output of 4. There we go. Alright. And now just give a rundown on breakdown of our following time and space complexity. The time complexity for our following solution is going to be O of n, where n is referring to the size of our given string, and therefore if the string increases, the time of a program also increases as well, so it's constant time. However, what's pretty efficient about this, given the fact that we're just using an array to start, and it's set to a fixed size of 26, we're not storing up anything else, we're just scanning, which is pretty useful for strings, especially if you're working with characters and the alphabet as well, which are just 26 characters. It's just going to be linear, which is pretty unique, because even though we're using a data structure, we're not storing necessarily everything. We're instead scanning throughout our entire array, which will actually make it very efficient to start with in terms of space complexity. So yeah, this is our solution over here. I'm just going to put the pseudocode up here. Start. There we go. So again, just give them the whole space and time complexity. The space complexity is linear because we have just 26 characters to start that we're just scanning through after we created our given array, which would be a vector in this case, which can be treated as arrays, and given the fact that we're just scanning throughout the entire string, and our array has just 26 of the characters that we're just scanning throughout the rest of our string, we will have a space complexity of linear, but again, time complexity is constant, O of n. Alright, so that was longest repeating character replacement. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe, and if you have any questions, feel free to put them in the comments section. As always, take care. Cheers. Bye-bye. Hello everyone, today we are going to be doing some Blind 75 C++ Leetcode, and today we are working on longest palindromic substring. So, before we get started, make sure we run out all the questions we need to answer. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique we need to use, what to do with the data, and what our output's going to be, just to give a whole walk down and breakthrough of the problem. Okay, so, given a string S, return the longest palindromic substring in S. So, overall, we already know what our input is. Our input's going to be a string of S. You can look at the parameters at the top. It's already highlighted up here. And then we need to return the longest palindromic substring in S. And to give a whole breakdown on everything, what is a palindrome? Well, a palindrome in particular is a word that can also, whenever you flip it, it would also be the same word at the same time, such as BAB would also be BAB, and then ABA would also be ABA. Now, what we need to do is that we need to find a way where we can keep track and count the number of times a character appears within our given string and keep track of every other one that has already been visited. But how are we going to do that? Well, today I'm going to introduce you folks to a concept called dynamic programming. For this problem, where dynamic programming is a method for solving complex problems by breaking them down into simpler overlapping subproblems, which are just breaking down. So imagine in yourself, instead of eating the whole elephant, you're taking bits and pieces of the elephant all together, so that way you can be able to structure out your problem. So it's taking the elephant bit by bit, and then you just expand upon the relationships over variables that you have already been given to start with, and what variables you can also keep track of. So what we are going to create, what we are going to do is that we will need to think of the string, and we would need to keep track of what we have already considered as well. So the first thing that's already going to be kept in mind is that we will create a vector where it will be a matrix to keep track of all the characters visited and if they are matching or not. The matrix will be called dp with n times n, and then what we are going to be doing is that for what we have already initialized when expanding upon the relationship, we're also going to have start and max length of our string, and then what we are doing with the following data, just expanding upon it, is that we will first loop through the string S from the end to start, because we're going to break up the string into two parts, and then in the next part we will from end to start, and in the same operation we will loop through the string S from the beginning to the end, and then we're going to check for every single character which has been visited and then visited. And we're not necessarily storing, since we are not using a data structure. Well, we are using a data structure, a matrix really, in this case, but what we are doing is that we're setting the conditions of the matrix to meet certain Boolean conditions where we will be interacting with every single other character when breaking up the string from beginning to end to ultimately check that it is a palindrome. So I'll expand that even further as well, and then in the final part, we will check to see if our matrix is true and the length of the current substring is greater than our max length. For if our max length is less than the current substring, we will update the max length, and because ultimately we want to return the longest palindromic substring that we have already found throughout the rest. Alright, so and finally what we will need to do is then return the longest substring. String. Alright. So we got 4 different steps that we need to break down. Let's get to it. Alright, so first things first, this is what we're going to do. We will first initialize our matrix, where it's going to be a vector, or hang on, prior to okay. I will actually, for sake of clarity, as stated again, we will initialize our string length, then we will, okay, there we go, that's a little better. Okay, so the first step and is going to be s.length right over here. Then we're going to create our matrix, which is going to be a vector. dp with n, and our vector, that will be a boolean, and n false. Then we're going to initialize our start, which will be 0, which is the beginning, and then our max length, which we'll set a default to 1 because every single string, every single palindrome needs at least another character inside. Then we're going to be looping through our string. So this is what we will be doing right here for int I is n minus 1, which is the string length minus 1. Since we're starting directly from the end, I is going to be greater than 0, I minus minus, since it's decrementing from the left side. And then we're going to set our matrix to true, given the fact that I and I would be a palindrome to start with, if both of them are the same. We will be iterating through our next step, which will be coming from the front. Int of j is going to be equal to I plus 1, since we are starting directly from the left-hand side, and then we have j is going to be less than the length of our string that we have, so it will be s.length, and then we will be incrementing j as well. Then what we will be doing, checking conditions for true for every character visited. These are the conditions we want. So if s of I is going to be equal to s of j, as a palindrome was already stated, and j minus I, given the, this is just where the value of our given character is, and if it's equal to the max length, which would technically be 1, or the matrix that we have, I plus 1, relative to j minus 1, since that would be technically the, when both of the strings have already met up to each other, since we're starting directly from the left and directly from the right as well. We would have dp of I and j be true. update our matrix as such. And then we will update our max length, where if j minus I plus 1 is greater than the max length, hence the characters that we've already done, we're going to update our max length accordingly, where it's going to be j minus I given its position plus 1, since max length was initially 1, and then the start is going to be equal to where I is located, because we can even have I, A, B, A already located at one point to another. And finally, what we will be doing, since we have that, we're going to be returning our substring, where this is going to be called from the STL library at return.substring, the start and max length. Make sure we got this right. Where n is the length right over here relative to our matrix that we have. For the sake of it, right. You can even do this for clarity at the same time. That's length. Oh, sorry about that. Right here, it would still be the same. Looks like it should be correct. Let's just make sure it's all good. Oh, hold on. So I'm going to be sure I clean up it all. I had a feeling there was something like that. Alright, it passes all the test cases. Uh-oh, wrong answer. Okay, I put a minus up here. It should be equal, which explains why. There we go. It passes all the test cases. Alright, and here we are. So let me just clean this up for you folks so that way you folks can understand where we are coming from. Alright, right over here. And so, just give a rundown on the space and time complexity of our following. Now, given the fact that we have nested for loops for the most part, our space complexity is going to be O. Well, first off, our time complexity is going to be O of n squared, given the fact that, one, we already have nested for loops where n is representing the length of the string, and since we're looping it twice, technically, initially, if we weren't looping it twice, we would need to have it be in constant space, constant time. And then with our space complexity, it's going to be O(n) squared, since we're using a Boolean matrix in order to keep the size of our following array. And since we are, one, scanning for the entire array, and then two, creating a substring as a result from it, our space and time complexity will be O(n) squared. So yeah, this was the longest palindromic substring. If you have any questions in particular, feel free to put them in the comment section. or if you liked and enjoyed this video, feel free to like and subscribe, and have any more requests or questions, feel free to put them in the comment section. Thanks again. Cheers. Bye-bye. Hello everyone. Today we are going to go over some Blind 75 Leetcode today, and the problem we are working with today for our Blind 75 C++ is longest substring without repeating characters. Now, before we get started, we always write out our questions of, we need to ask ourselves, what is the input, what data structure / algorithm / technique we're going to use, what to do with the data, and what our output's going to be. So, to be able to give a breakdown, given a string S, find the length of the longest substring without repeating characters. So, based on the question, we are given a string, and then what we need to do with the data is find the length of the longest substring without repeating characters. And then we'll go over the examples. So, in terms of the behavior we need to replicate, say for instance we are given a string of ABC, ABC, BB with an output of 3. The answer is ABC with a length of 3 because we have 1, 2, 3 unique characters within our string that are not repeating. And it seems as if that we keep a count, or we keep a record of any character we have visited if it's unique. And if it's not unique, then we will break off the entire substring. And let's go over example 2. We have B, 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 B with an output of 1. The answer is B with the length of 1, hence right over here, pretty straightforward. And for this one, P, W, W, K, E, W with the output of 3. The answer is W, K, E with the length of 3. Right here. And notice the answer must be a substring, and it cannot be P, W, K, E. Hence, because we have another character that is in between P, W, and K, E. So, with our following output we have here, and S contains English letters, okay. So, be able to break down over the questions we have already answered. So, we already know what our input's going to be from our question. You can even look at the parameters at the same time to discern what our input's going to be. It's a string. And then we already know what we're going to do with the data. We need to find the length of the longest substring without repeating characters. And for our output, as highlighted by the example, we will return an integer representing the number of unique elements we have visited in our string. What is the longest substring with unique characters? Those are our questions that we would have. And so the technique I'm going to introduce you folks today is going to be called the sliding window technique, where unlike binary search, where it's divide and conquer method, and you have 3 different variables of a low, high end, and a middle, and then you find one area and then cut off another area until you found the specific element you're looking for. And it's not the 2-pointer technique, where you just have 2 variables, a low and a high end, where in your sliding window you are given a range that you also need to figure out within a data structure you're trying to scan through, like an array. The sliding window technique has 2 points, and then also has a length that one could already set. So there are 3 variables one must construct, which include a low, high, and maximum length for the sliding window technique. And with our sliding window technique, we will scan through our array to keep track over the number of unique characters we have visited through our array, and how we're going to keep track of everything. So a data structure that we can actually use for this is called a set, where a set sort of behaves in a case like a map. Just the only difference is that you don't have 2 values, you have 1 value. You keep track of. And we're going to use the set to store all the unique characters we have visited using the sliding window technique. And so I'm going to go over the steps over what we need to do for what we are going to do with our data. So first things first, we are going to initialize 2 pointers at the beginning of the string, which will represent our low and high, which will represent the left and right. You can call whatever you want. You can call low and high, but for the sake of what we're doing, we're going to call this the left and the right, which will be representing the beginning, the left, and then the right, the end of the string. And then we will have our and initialize our maximum length which will be a variable. The low, high end, so the left and the right, along with our max length, is going to be for our set. We're going to use the set again to be able to store every single character. Use the set to store every single character we visited with our from our string. There we go. And then also we would initialize our set. And so what we will be doing then is that we're going to use a while loop in this case. So while, and then in this while loop we are going to expand upon the relationship of our 3 variables that we have already created between our low, right, and our max length. So while initialized variables, we will expand upon the relationship of them relative to our string. So in this while loop that we're going to create, we will have right being less than the length of the string, because we're scanning throughout the rest of the array. And then what we will do is that if the string is, if we are at the end of string, in string we stop scanning. So basically what we will be doing is we will be extending the right pointer until we find a repeated character or reach the end of the string. And then for every unique character, we will add it to the set. And our right variable is going to represent our counter. And then what we will be doing is that we will update the max length if the current length of the substring is larger. And then if the character is already in the set, remove characters from the left until the repeated character is eliminated, so that way we can check to have unique characters. And the max length is what we will be returning. So now just write down everything that we have done so far. Just gonna put this up here to organize. So first things first, what are we going to do with the data? And then our output as well. So first thing we will do is we're going to initialize our left, right, it's going to be 0, and then int max length 0, and then initialize set, should be set car, make a set. So while the right, we have to expand upon the relationship between two. Length, which is a method called upon from string. We will extend the right pointer until you find a repeated character. So what we will be doing is that we're going to be calling on this method called find, where find is sort of like a for loop in of itself for a set, except for the difference is it's much more efficient and it's within the context of our set. So whenever you're scanning an array, instead of having a for loop, you can use find to be able to call upon which element you're trying to find within the data structure you're trying to scan through. So find right, I'm sure it's gonna be fine. All right, that's how you're able to get there. Just want to be sure I got this right. Make a set end. All right, make sure I got the syntax right. Now we're going to insert the unique character in our set. Then we're given string. And then we're going to update the max length. Where our max length is going to be equal to max of max length, and make a set size, which is a method called upon from the STL library for set, and then we'll have else ready in the set, remove characters from the left until repeated character eliminated. Make a set dot erase left. All right, and then finally we're going to return our max length. I want to be sure I got this right. Should be less than. Alright, passes all the test cases. Alright, and it works pretty well. Alright, so just to give a rundown over exactly how our following technique is able to work is that the time complexity for our solution is going to be O of n. To start is that n is representing the length of a given string, and therefore it runs in constant time. And then for our space complexity, the space complexity is going to be pretty unique because it is going to be O of min m of n, where m is the size of the character set, and in the worst case scenario, the entire string would have distinct characters, and the set would then contain all the characters, hence the space complexity would be O of n altogether. But again, we have a worst case scenario, and then we have And our space complexity is going to be O of min, M of n, where M is the size of the character set. However, in the worst case scenario, will be O of n altogether. So it would be unique, but again, it's relative to the character size at the same time that we are also adding upon. So our best case would be O of min, M of n, and then our worst case would be O of n. So yes, this was longest repeating substring without repeating characters. Thank you again for taking time to watch this. If you enjoyed this or have any questions, feel free to put them in the comment section. And as always, yeah, take care. Cheers. Hello everyone, today we are going to be doing some Blind 75 C++ Leetcode, and today we're working with Palindromic Substrings. So, to be able to kick things off over what we need to do, we first need to have our 4 questions laid out, asking ourselves what the input's going to be, what the data structure / algorithm / technique we need to use, what to do with the data, and what our output's going to be. So, first off, breaking down the question, to answer our question with the input, given the string s, so we already know exactly what our input is, we need to return the number of palindromic substrings in it. So a string is a palindrome when it reads the same backwards as forwards. A substring is a continuous sequence of characters within the string. So we need, it looks like, especially from example 1, where we have A, B, C, there's an output of 3. There are 3 palindromic strings, which are their own separate characters. And example 2, we have A, which has a combination of 6 different palindromes which can be made from this string. So return the number of combinations of palindromic substrings. And a palindrome is, as stated before, is when it reads the same forward and backwards. It's like damn it, I'm mad. Spelled backwards is damn it, I'm mad. Like same way. Just same amount of characters in the string accordingly, forward and back. All right. And so this type of problem for palindrome dynamic programming is a popular technique that we would use for our solution. And I'm just going to go further in depth inside the steps of what we got to do. So breaking down, first thing we need to do is that we need to initialize the string length and the matrix that will have the string length on the inside to check to see if there is a palindrome. If so, it will be true. This may be a little bit confusing and for the first step, but what I mean by the first step to start is that we are going to be creating a matrix, and I will write this out after we go through the steps. So the first step we will do is that I'm going to have n be equal to s dot length right here, and then we're going to create our matrix over here. We're going to initialize our matrix where it's going to be a vector bool. It's going to be a matrix accordingly where it is actually n, which is the size of our string, vector boolean n false right here, and this will represent and n represents the size of our given string that we have, and we're checking to see by using this matrix throughout each of the steps that we will be doing, because we're going to be looping through our entire string to check for palindromes. We'll be using this to keep track of if there is a palindrome or not. Okay, so for the second step of what we need to do is that we need to create a count as well. And then for the third, we're going to iterate through our string s. Two. So I'm just going to do that. We're going to create our count to keep track of the number of palindromes on the inside and first initialize. And then right through our string, we'll be iterating backwards and then iterating forwards. And while we're iterating backwards, we're going to set that our matrix to true to start, since we need to count for the single character. that we will have. And then we'll increment our count for need to return how many palindromes are inside of our string. And then we're going to iterate forwards, and while iterating forward, our condition is going to be, we will check to see if the character at index I, s of I, is the same as the character at index j, s of j. Since j is going to represent the index that we will be going in a forward direction. And then we will be checking the length of the substring. And if the characters are the same, and if the length of the substring is 2, then it will be a palindrome. And 3 palindrome, and this part is just going to be one continuous line if statement that's going to have different parts of it. So I'm going to go back and then we'll further expand upon that part for 3.2.2. So let's just go back on 3. We're going to iterate backwards. So for int of I is going to be n minus 1 because we're iterating backwards. I is greater than or equal to 0. And then I is decrementing backwards accordingly. And then we are going to set dp for true right over here. And then we're going to increment our count. And then we're going to be creating our second for loop where j is going to be equal to I plus 1, referring to the next index that we're referring to. J is less than the size of the string, hence n right here. And then j is incrementing as well. Then what we will be doing is that now continuing on the subsection for 3.2, we're iterating forward, is that we will be checking 3.2.1 is referring to s of I is equal to s of j. And this part, maybe a little bit tricky, is going to be j minus I, which represents the index in the forward and backward direction to see if it's 1, or the matrix that we have with our given index accounting for where our initial point is relative to our backwards point right here to see if there is a valid palindrome. If there is, then we're going to be returning true with respect to two different ones. Like for instance, if we have A right here or this one right here, or we can have BAB. We already know that I would represent this B and J would represent this B over here. And we'll increment our count after we set this to true. And we have done so to keep track of everything. And then finally what we need to do is return the count. Let's highlight right here. Let's make sure we have everything already set in place. Make sure everything's already initialized. Right here, double check. I think we should be good accordingly. All right, woohoo! We passed all the test cases. Now, let me clean this up for you folks so that way you guys can get a better look of our entire solution. Awesome job. Woohoo, yeah. There we go. There we go. Bam. Right here. step 1, step 2, step 3, then step 4. There we go. Let's make sure it's all right. After all the cleaning, boom, we got it, and ta-da! And wow, that's pretty good. All right. Now, just to give a whole rundown over space and time complexity that we have for the following is that our time complexity, given the fact that we have 2 nested for loops to be able to start, but we are also given a string with a given amount of size. So, given the fact we have a nested for loop to start, and this is accounting for scanning the array twice, we would have a time complexity of O of n squared. Now, mind you, since we also have a Boolean matrix that we are storing, 1, the conditions as well as the characters, we will have a condition of O(n) squared. And the following solution is already efficient in terms of time and space complexity, since we're using dynamic programming to avoid any redundant computations altogether. So yeah, this was Palindromic Substrings. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And also, if you have any questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we're going to be going over some Blind 75 C++, and today we are going to be focusing on meeting rooms. So, before we get started, to break down every single problem, let me just put this up. Alright, so we have interval. We need to ask ourselves what the input is going to be. What data structure / algorithm / technique we need to use. What to do with the data. And then what our output is going to be. We need to answer all those questions, all 4 of them, so that way we can break down and understand fully. Because sometimes there are going to be some questions that are going to trip us up, as usual, in said interviews. Alright. So, to be able to go over the question, given an array of meeting times, intervals, where interval I equals start I, end I, determine if a person could attend all meetings. So interval, we have array of intervals, as even indicated by right here, up here in the parameter. So let's go over the example. Example, we have interval of 0, 30, 5, 10, 15, 20. Where intervals I equals start I, end I, determine if a person could attend all the meetings. Well, the question is, can the person attend all meetings? Okay, so to be able to give a rundown of this whole thing and to be able to break up the question is that, so if we have intervals in particular, so the meeting is going to be starting at this time and then ends at this time, starts at this time, ends at this time, starts at this time, ends at this time. As a result from this, given the fact it's overlapping the other times, therefore it's going to be false. But then, for example 2, we have 7, 10, 2, and 4, where it looks like it's just for 3 hours over here, and it looks like it's 2 hours over here. They don't overlap, so it's going to be true. Okay? So, to be able to go further down over what we will use, the data structure we will be using is going to be a min heap, which is built using a priority queue, where that is the principle of last in, first out. Much like in the grocery, it's first in, first out. Sorry on that. Priority queue, or queues in general, is first in, first out, much like in the case of the grocery store, for instance, and shopping cart. That's the best way of metaphorizing it. And so what we will be using this to sort the intervals. Alright, here we go. And then we need to ask ourselves what to do with the data. Okay, so what we need to do with the data is first sort the intervals based on their start times. Then we will iterate over the sorted intervals, adding each interval to priority queue min heap. Okay, just clean this up. Alright. If the start time of the current interval is greater than or equal to the smallest end time, the root of the min heap, we can use the same room and pop the end time from min heap. Alright, here we go. Right over here. And fine, we're just going to output. Put whether all the meetings can be attended or not. So, to be able to give a rundown on this whole thing, we're going to focus on step 1. Again, intervals. And right over here. Then we're going to have step 2, where we're going to create a priority queue. Int vector int greater int min heap accordingly right here. Okay, such as we have a following vector of our int here, and that because a priority queue typically has 3 different parameters on the inside. Now we're going to iterate for auto and intervals. Checking to see if it is not empty, if the min heap is not empty, and the interval at the very first index is greater than or equal to the min heap at the top, we're going to pop it. It behaves similar to a stack, but then we have other characteristics of the min heap. Min heap dot push. We're going to push this inside interval the next index. One will return false if min heap size is greater than 1. We're going to return false in this case is one of the edge cases. And finally, by default, we will return true. That's because we are comparing the different sides of our following heaps inside of the following interval that we have. So just going to check to see if everything already matches up. It passes all the test cases. Let me clean this up for you folks. Submitting it. Alright, and it works. So to be able to give a rundown and break down everything that we have, the time complexity for our following solution is going to be O n log n, where n is the number of intervals, and due to the sorting step in the beginning that we have, since we have different intervals on the inside of the whole intervals array, that would explain what we have, and then given the fact that we're using a data structure of a queue, the space complexity is going to be O of n, since we need to store all of the intervals that we have visited and compared. But overall, just the storing aspect is going to have a space complexity of O n. So yeah, this was meeting rooms in C++, Blind 75. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any questions, put them in the comment section. And as always, take care. Cheers. Hello everyone, today we're going to be doing some Blind 75 C++, and today we are focusing on jump game. Now, before we get started, we need to know how to break down our problems, so I'm going to write out our 4 questions of what we need to go over. You need to ask yourselves what the input is, what data structure / algorithm / technique to use, what to do with the data, and then what our output is going to be. So, pattern accordingly. So, you were given an integer array nums, already up here, it's highlighting the parameter, okay. It's called nums. You were initially positioned at array's first index, and each element in the array represents your maximum jump length at the position. Return true if you can reach the last index, or false otherwise. So, going over the example 1, is it possible to jump from one index the very first index and all the way to each element accordingly. Okay, and each element in the array represents your maximum jump position. Okay, right here. Okay, yeah, right there. That's pretty straightforward. So we have this 3, 0, false. You can't because it's 0. Makes sense. All right, and the jump, for output, it's going to be return true if we can make the jump, false if we cannot. So looks like for this entire thing, we will be using the greedy algorithm. And what are we going to do with the data? Well, three, 4, 5. Alright, so, we need to, overall, traverse the array from right to left and maintain a last position, which is initially the last index, and then if the current index plus the value at the index is greater than or equal to the last position, we update the last position
to be the current index. So how are we going to do this? Well, based on the number of steps we are going to do, which is going to be 4, we're going to initialize the last position to be the last index of nums, and then we are going to traverse through the array from left to right, and then if the current index plus the value at that index is greater than or equal to the last position, update last position to be the current index, so that way we know exactly if we have attained our maximum jump. And then finally we will return true if the last position equals 0, otherwise false. So we're going to first do our last position equals nums.size minus 1. Over here, then we're going to do step 2. We were going to iterate through our entire array. 0 is going to be equal to nums.size minus 1, since we're going from the rear, equals 0, and then I minus minus over here. Then step 3, if I, like for example, hang on, I'll write this out and be able to showcase what we have. I is going to be greater than or equal to last position. Then we're going to have last position equal I, which is the current index. Finally, return the last position equal to 0, where by default booleans will be true in C++. Okay, so it's pretty self-explanatory over what we have, since the reason being that we're starting from the very last index is that in order for us to be able to get our maximum what we're trying to do is determine if we, from the very last index, if the jump can be made. So if we were to have, for instance, in one example, we'll put this in here, such as if we have the value of the index of 1, 2, 3. Let's make this 1, 2, 3, 2, 4. We'll determine if it's true. So I, in particular, starting from the very last one, if nums of 1, 2, 3. If we have the third index, since arrays typically start at 0, 3 plus nums of 3, which would be 4, equal to last post, where if it's a num.size minus 1, right over here. So nums.size would actually be 4, since we have 4 different elements inside, minus 1, which should be 3. So therefore, since we already have 7 is greater than or equal to 3, we are going to be returning true, and the conditional logic already makes sense over here. Everything's already initialized. Smooth that. Alright, and it works. I'll just clean this up so that way folks can be able to see throughout. Alright, and we are good. And now, just to be able to give a rundown of our space and time complexity over what we have. So, given the fact that we're using a greedy algorithm, they're naturally pretty efficient in terms of space complexity because they just scan throughout the rest of the array. The principle behind it mostly focuses on finding every single possible element that we have in our given array or data structure. And since there's no data structure to be able to store any of the information that we have passed through, the space complexity is going to be linear, O of 1, while we are running in constant time O of n because n represents the size of the array. So yeah, this was Jump Game on C++. This is another subfield of dynamic programming as well. Thank you again for taking time to watch this. If you have any other questions in the meantime, feel free to put them in the comments section. And if you also like this, feel free to like and subscribe. And as always, take care. Cheers. Hello everyone, today we're going to go over Sublime 75 C++, and today we are going to be focusing on how to find the maximum depth of a binary tree. So, before we get started, always breaking down the question, we need to ask ourselves what the input's going to be, what data structure / algorithm / technique we need to use, what to do with the data, and what our output is going to be. So, going over the question, given the root of a binary tree, return its maximum depth. Okay, so we are given a tree, and we need to return maximum depth. And so the technique we're going to be doing is depth first search. Hence in the name, it's useful to find the depth. And then there are typically two techniques in trees, breadth first search and depth first search. Depth first search utilizes more of a stack. Breadth first search uses a queue in this case, but C++ and their STL library is very intuitive when it comes to their own library, and so we'll just be focusing on leveraging on that. And it's really 4 easy steps to go over, so it's going to be really fast. So the first step we're going to do, we're going to have our edge case when we don't have any value in the root. Root is equal to null. Second step we will have is calculate the maximum depth of the left subtree. Then we'll do the same for the right. Finally, return the max depth of both the left and right subtrees plus 1 to include the root. Alright, so this will be straightforward. So if root equals null ptr, we return 0. Since we don't have anything in here, and we are returning a number, and then with step 2, the maximum left, so int left is going to be equal to the max depth of root of left. And we'll do the same thing for the right. And finally step 4. Just gonna make sure we have everything already set and it is right. Alright, passes all the test cases. And here we go. Woohoo, that was quick and efficient. Okay, just be able to give a rundown and breakdown of everything we already did. So, the time complexity for our following solution is going to be O of n, where n is representing the number of nodes in the tree to start, and that we are finding both the right and left depths of our following tree. We have to keep track of all of the nodes that have been visited to be able to get our max depth. And then the space complexity is going to be O of h, where h is referring to the max height or max depth of the tree overall, and so we need to store those values accordingly, so that way we can be able to have our following solution of getting the max depth of our tree. And I realized I made a spell check error in my front. I will fix that. A couple of them. I apologize for that. I know it's kind of dumb. And here I am running test cases when I'm just doing the comments. I'm just trying to make sure this is all clean. So, yeah, this is pretty much it. This is finding the maximum depth of a binary tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And then if you have any questions, please put them in the comment section. And as always, take care. Cheers.
Hello everyone, today we will be going over the blind 75 in C++, and today we are working on Kth Smallest Element in a binary search tree. Now, before we get started, feel free to pause the video to take some time to look over the questions over what we need to do to break down the problem. First, we got to figure out what the input is going to be, what data structure / algorithm / technique to use, what to do with the data, and then what our output is going to be. So, to be able to break down the problem, given the root of a binary search tree and an integer k, return the kth smallest value, 1 minus index, of all the values of the nodes in the tree. So, based on the problem, and we can even look at our parameters at the same time, we have tree node to root, and then we also have this as well. We have our input of a root of a binary tree and an integer k, where it looks like, just from breaking down the following problem. So the problem is asking us, we need to find the smallest value, 1 minus index, of all the values of the node in the tree, but we have to be at this kth. So what does that mean in particular? Because this question can be a little bit tricky. So if I were to explain this even further, for example, so say for instance we have this binary search tree that we have of, I'll just put it right over here just for safe measure that we have. So we have a root 3, 1, 4, null, and then 2. Then we have k is going to be equal to 1. What it's asking us to do in this case is to take all of the elements which are right here. So we would have, we have this accordingly, and we are going to sort them out first. So we have 1, 2, 3, and 4. And it's asking us the smallest element throughout the rest of our binary search tree that we need. It's just, alright, and our output for this one will be 1 accordingly, because the value that we have at 1, that's the smallest within this area, is 1. Now if we were to go over the second example, if we were to have root for this following binary search tree, and then we have k, what we need to do for this specific problem is that we need to first sort everything out, 4, 5, 6, and then we also have null and null, but really we're just focusing on the following numbers right here, and those will be gone. So what we need to do is that we need to find the third smallest element accordingly, and so our output would be 3. That is what they mean by the kth smallest value at the following indexed. So what we need to do is that we need to find a way where we can, 1, sort all the values within our binary search tree, and then according to k, find the kth smallest value which is indexed at the given position. So if we were to have, for instance, k be 4, for example, the solution would be 4. But our biggest problem that we have is that we have a given binary search tree that's not in order. So I'm going to introduce you folks to a technique that we would use, and I'll just get rid of this for the sake of clarity because we can look at the examples over here to further understand. The technique I'm going to be introducing you folks to is really going to be using a in-order traversal. Where in-order traversal, what it's supposed to do is that it starts from the very leftmost type of element accordingly, then it goes to the root of the following tree, and then heads over to the right accordingly. Because in a binary search tree, the way we divide up each of our numbers accordingly is that typically most of the values that we have are that are less than the root of a given tree are going to be on the left, and the ones that are on the most on the root of the binary tree are going to be on the right side. So we already recognize this behavior that we have, for instance, of 3 since 2 is less than 3 over here for binary search tree, it's going to be our left-hand side. And then since 4 is more than 3, it's going to be our right-hand side. That's just by principle of binary search trees, namely. And so in order traversal, just be able to write out the method for it, is that we're going to find the left node. Then we're going to go back to the original node, or the root node, per se, just for the sake of clarity. And we're going to be going through every single subtree accordingly for our technique. Then we finally head over to the right, so we can sort all the numbers accordingly. Because first what we need to do, and I'm just going to put it back on, if we have this, or over here, we got to sort it to 1, 2, 3, 4, 5, 6 to find our output of the third kth smallest element. So it would be 3. We are just trying to replicate this type of behavior accordingly so that we can figure out how to sort our binary tree, because one of the biggest issues that we have is that our given data that we have is not even sorted. So we need to find a way to be able to sort it. And we're told that it's a binary search tree. So we will be following this pattern accordingly. And now, oh yeah, I will write out the output. We need to return the smallest output based on k accordingly. Okay, so now to give a breakdown on the following steps that we need to do is that I'm going to first write this out in 4 steps, so that way we know exactly what to do, and then I'm going to be expanding further on our 4 steps as well. So what we will be doing here is that for our first step, we're going to focus on our edge case for trees, is that we're going to initialize a variable count to 0. And then what we're going to do is that we're going to be creating a function called InOrderTraversal, which will take in the root of our given tree, the k element that we have, as well as our count, which will represent our number of nodes that we have accordingly while we are going through the rest of our tree. And so once we have done that, we're going to go over to step 3 for inside our InOrderTraversal function. And I'm just putting it right here. Okay, what we will do is that at each visited node during the in-order traversal, we're going to increment our count by 1 to indicate we have visited. But then next thing we'll do is that we are going to have the edge case where if we have a node be null, we will return the value indicating it's not found. We'll be treating it as return -1, given the fact that we are working with an integer in this case for a function. And then what we will be doing is that we will be doing in-order traversal by creating our left node, which will be treated as in order traversal. We're going to do a bit of a recursive call, node, left, k, and then count to keep the parameters accordingly. And then what we will be doing is that if there is no null value for the left node, we will return our left, then we will increment our count. And then what we will be doing accordingly is that if the count becomes equal to k, we will return the value of the current node as the kth smallest element, because we can neglect all the other ones as well, because we only care about our kth most element that we would have. And then finally we would be, what would we do is that we can do a recursive call again, but for the right hand side, where we'll be doing this over here. Let's make this as 4, but it's still technically in there. I just want to be sure on this. Yeah, it's still in there. So I'm just going to make this as 3G, do a recursive call, but you have the right side of in right. So that's how we will do it. And given the fact that we are just returning our following, what we will be doing is that this will be our output. Okay, now just to be able to write up everything else. So for step 1, we're going to first initialize the count, which will indicate the number of nodes we have seen. Then what we will do is that this will be our output. We will return the value from an in-order function, reversal. Yep, so we will have root, k, and then count. Accordingly, now what we will do is going to put this up here for the sake of clarity, keep it all clean. I'm going to create a private function accordingly. So private int in order traversal tree node int k int and count. This is all the fun part, so this is going to be 3. Yep. So you'll have 3A, 3B, 3C, 3D, 3E, 3F, 3G accordingly, just to organize it all together. Remove the white space for clarity. Alright, so for 3A, what we will do is that we're going to focus on our edge case right over here. If the node is null, we're going to return -1 as our edge case that we have. And then for 3B, I apologize for this confusion over here. I will make this, I'll make this 3A to start with, just for the sake of clarity. I'm also going to put these in the comments as well, just to clarify on this. There we go. That's better. Okay, so for 3B, then we will have int left. It's going to be in order traversal node left k and count. Then if left doesn't equal -1, that means there's a value that's right there. We're going to return left. Yep, in 3D, we will increase our count accordingly. Alright, if the count will be equal to k, we'll return node value right over here. And then what we will do for this part is then return the in order traversal for our node on the right k and count accordingly. Alright, just making sure I have all the steps needed prior to. So we have left, we're going to increment our count. Yes, it's already there. Node val. Okay, it's right there. So again, apologies for the confusion on this. I'm going to put this solution in the comments so that way you can be able to walk through each step accordingly and be able to take this with you to further understand. Let me just run this to be able to make sure that everything is correct. Namely, I'm just going to move all this out. You folks can actually understand and see the whole thing. And then our output. There we go. Alright, it passes all the test cases. That's good. And time to submit. Ta-da! Okay, this is great. This is great. And again, the solution will be entirely in the comment section. So, to be able to give a breakdown on our time and space complexity for the following. So, our time and complexity for the solution is going to be O of h plus k, where h is representing the height of the binary search tree, and k is our given integer. When we have a worst case scenario where the binary search tree can be skewed, resulting in a height of n-1, where n is the number of nodes in the tree. And our space complexity for a following solution that we have is going to be O of h, given the fact that, one, what we are doing is that we are keeping account of everything that is being accounted for every node that we have visited. So therefore, relative to the height of the binary tree, our space complexity is going to be O of h. So yes, this was Kth Smallest Element in the binary search tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we will be going over the blind 75 in C++, and today we're working on lowest common ancestor of a binary search tree. Now, before we get started, make sure that we have our 4 questions that we all need to lay out accordingly. Let me just do one. We have our second, third, and fourth. We need to ask ourselves when breaking down the question what the input's going to be, what data structure / algorithm / technique we're going to use, what to do with the data, and then what our output is going to be. So now, breaking down the problem, given a binary search tree, find the lowest common ancestor node of 2 given nodes in a binary search tree. Okay, so we are given a binary search tree with the root, P and Q, which could represent the 2 nodes. And it looks like that we need to return the lowest common ancestor. And according to the definition of the lowest common ancestor in Wikipedia, the lowest common ancestor is defined between 2 nodes, P and Q, as the lowest in T that has both P and Q as descendants, where we allow a node to become a descendant of itself. Okay, so now, to be able to just break down everything that we have already just been discussing over here. So if we have our input right over here, root is equal to 6280479, and then null, 3 and 5. Then we have P
equal to 2, and then q equal to 8. Lowest common ancestor of nodes 2 and 8 is going to be 6 over here, given the fact we are working with a binary search tree. But then if we have the root of 62804790035, p and q, 2 and 4, 2 over here, and then we have 4. Accordingly, what is the lowest one that we would actually have this relation to? Well, according for this one, 2. The lowest common ancestor of nodes 2 and 4 is 2, since a node can be a descendant of itself according to the lowest common ancestor definition. Okay, so 2 and 1 accordingly. Alright, so it looks like that the lowest common ancestor refers to the root at the highest level possible. So meaning in particular that if we have, for example, 6 over here, p and q, 2 and 8, they are both descendants of 6. The definition states the lowest common ancestor is defined between two nodes and the lowest node in T. That means that p and q are descendants of it. And if 4 is a branch of 2, that means 2 will be the lowest common ancestor. Okay, so we need to replicate this behavior for the lowest common ancestor. Just clarifying on this. And so what we will be doing for our following steps accordingly is that from this we will be extrapolating on binary search tree properties upon the relationship of the nodes we have, and in doing so we will traverse the tree and compare the values of the current node with the values of p and q. Alright. And so, just to be able to go over the steps, we're going to first have our edge case that we need for the following. It looks like for the tree, what we would need to do is that, well, since we're already given a binary search tree, let me see if there are any other constraints as well. P does not equal to Q, and P and Q will exist in the binary search tree. And all the values of the nodes are going to be unique in this case. Okay. So, for an edge case that we would have, we will need to return a null pointer if we have a null root slash node of the tree. That will be our edge case. And then what we will be doing next is that we will start traversing the binary search tree from the root, assuming we have a value. Then what we will be doing next is that while traversing, we're going to compare the values of the current node with the values of P and Q. And then, if both P and Q are smaller than the current node value, we're going to move to the left child. Then if both P and Q are greater than the current node's value, move to the right child. And then if neither of the above conditions are true, it means the current node is the lowest common ancestor, which means therefore return the current node in those edge cases. So we will have it from the left side, right side comparison. And so now to be able to just go over the steps, step 1, step 2, I'm going to leave step 1 over here to start with, and what we need to do in this case, I want to put step 1 over here, and we will be returning a null pointer just in case. I know this may be a little bit tricky at first, but then what we will need to do is that it will help us expand more upon our relationship. So the first thing we will need to do for step 2 then is we'll have tree node will represent the current node. Yeah, okay. It's going to be the root. And while the current node doesn't equal null pointer, we're going to expand upon step 3, step 4, step 5, and step 6. So step 3. Okay. Step 3. We're going to compare the values of the current node with the values of P and Q. So that means P's value is going to be less than the current node, which would have the value, and P will be the value where we are comparing the current node with its value. Just want to clarify that so that we have P and Q for them. Yep. I'm sure I got this right. There we go. Now for the next step that we would need is that we're going to be setting step 4. If P and Q are smaller than the current node's value, move to left child. So that means current node accordingly. So we have this case over here. This will be step 3 actually. This will be step 4. Yep. Since we're making our comparison accordingly, if we have current node is going to be current node to the left. Okay, now, and then this will be step 5 accordingly for this edge case. Where it will be the same, except for it's going to be greater than. Right over here. That current node is going to be the current node on its right. And then for step 6, what we would do is that we're going to have our else case. Then if neither of the conditions are true, we then assume that we have the current node be the lowest common ancestor accordingly. So just want to be sure we get everything right. Yep. And then, yes, no pointer right here. I'm just going to clean up the rest of the notes for you folks so that way you can see it thoroughly. Mm-hmm. Accordingly, and I'll have these in the comment section as well, so you folks can also follow along. Let me just double check to see if it's all right. We compare the left, and then we compare the right, and then we assume at the same time, okay, in the worst case, we'll return null. Okay, I have an extra bracket that's already right here. Yeah, not needed. Not needed. Yep, okay. Alright, passes all the test cases. Alright, and it runs efficiently. So to give a breakdown on the space and time complexity for our following solution is that our time complexity is going to be relative to the height of the binary tree, so therefore the complexity for our solution is going to be O of h, given the fact that we are currently storing the value of a current node accordingly, so that's why it would be constant, and it's all relative to the height of our tree to be able to find our lowest common ancestor. And luckily, since we are not using a data structure to be able to store our given values, our time complexity for the following is going to be O of 1, since the algorithm only uses a constant amount of extra space for storing the current node and just compares the values accordingly, since, again, we're not using another data structure. So yeah, this was lowest common ancestor of a binary search tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you also have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to be doing some blind simplify C++ Leetcode, and today we are working on meeting rooms 2. So, before we get started, just got to answer the 4 questions what we need. You need to ask yourselves what the input is, what data structure / algorithm / technique we need to use, what to do with the data, and what our output is going to be. So, to be able to kick things off and get things started, so, given an array of meeting times intervals, where intervals start I and return the minimum number of conference rooms required. So, we are given an array of interval times. We need to return number of conference rooms required, and in this case, we're going to use a min heap, which is which is a priority queue. What to do with the data. So to be able to figure out what we will be doing with the data, we're going to break it up into 4 different steps. 1, we are going to sort the intervals by their start times. 2nd, we will initialize a min heap to keep track of all the end times of the meetings. And then 3, for each interval in the sorted list of intervals, if min heap is not empty and start time of the current interval is greater than or equal to the smallest end time root of min heap, we're going to pop the end time from min heap, and then we will add the current intervals end time to the min heap. Then we're going to output put size of the min heap. That's pretty much it. It's going to be asking just overall, based on the following times, how many meetings there are in total. The minimum number of conference rooms required. So it could be intervals, for instance, on if we have 2 meetings going on at the same time within a given context, like for instance, 5 and 10 fall in 0 and 30. or 15, 20, we're going to need at least 2 conference rooms for the star. And in this case, we can have 1 to begin with. So let's kick things off. Step 1, we're going to sort. Let's begin. Intervals end. Just calling upon from the STL library, we're going to create a priority queue. Then we're going to loop through part A. If not, min heap. If the min heap is not empty, and the interval at the very first index is greater than or equal to the min heap at the top. We're going to min heap. We're going to pop the heap. And then we're going to add the current element with the min heap. And then finally, we're going to output the size. So we're going to return min heap dot size. Forget the comma. Alright, passes all the test cases. Let me clean this up for you guys. There we go. Alright, and it works and passes all the test cases. So, to be able to give a rundown on the space and time complexity, the time complexity over min heap overall in solution is going to be O(n) log of n, given the fact that we are looking throughout intervals. Within our intervals array, where n represents the number of intervals, and this is also due to everything being sorted. And then we're going to have a space complexity of O(n) because we are using a queue to be able to store everything. And so, yeah, that is pretty much Media Rooms 2. For the most part, it's pretty similar to Media Rooms 1. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe. If you have any other questions, please put them in the comment section. And as always, take care. Cheers. Hello everyone, today we are going over the Blind 75 in C++, and today we are working on non-overlapping intervals. Now, before we get started, make sure that we have our 4 questions already labeled out. Feel free to pause the video to write them down if you're following along. We need to ask ourselves what the input is going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. So, to be able to give a breakdown on the following question, given an array of intervals, where intervals I equals start of I, end of I, return the minimum number of intervals you need to remove to make the rest of the intervals non-overlapping. So, if we were to go over the examples that we have, we'll be able to get an idea. However, one thing that we should take into consideration is that we already know exactly what our input is going to be. We are given an array of intervals. You can even look at the input up here in the parameter. And then it looks like we need to return the minimum number of intervals you need to remove to make the rest of the intervals non-overlapping. We will expand upon this. And just to give a visual example over exactly what they mean, let's go over the examples. So, if we are given an array of intervals, for instance, our output is expected to be 1 in this case. And the reason being, as they state, is 1 and 3 can be removed and the rest of the intervals are non-overlapping. So if we have all of the numbers inside of our intervals array. So we have 1, 2, 3, and 4 for the most part. And what it looks like if we were to remove this overlapping interval that we have, 1 and 3, because if we were to scan the rest of the numbers, we see 1 and 2 is inside of 1 and 3, and 2 and 3 is also inside of 1 and 3. So highlight the numbers to visualize the relationship between all the elements and for our input and output. And if we were to go forward on example 2, we have, so in this case it makes sense over exactly why the output would be 2 in this case for the minimum number of intervals we have to ultimately get an array that would have intervals where all the numbers are non-overlapping. And we need to return the number of intervals one needs to remove to make the rest of the intervals non-overlapping. And for example 3, it looks like between 1 and 2, 2 and 3, 0, because even though it may appear at first, if we were to expand more, based on this example, and our output is 0, the reason being is, hey, we have 1, 2, and 3, 1 and 2, and 2 and 3, even though they're connected by 2, they're not overlapping technically. It's really just in the case like this one, for example, 1 through 3, and then we have 1 and 2, where we have a number inside of our interval. Overlapping is when we have a number inside another number inside our interval. And so the technique that we will be using, that I'll be introducing to your folks for our solution to be able to solve, is going to be a greedy algorithm with sorting. And what I mean by that is that a greedy algorithm is more of a technique, really, that explores all the possible relationships within a given series of elements that we are given. Meaning that if we, for instance, are given an array, we need to discern exactly the relationship from all of the elements and all the possibilities that are possible. And this is typically widely used if one's just trying to figure out exactly, hey, if we have this set of these set of elements, what's the relationship between them? And we're going to be implementing a sorting technique first to organize all the intervals all together, because we know that we know our start and end numbers are going to be different in relationship. And we're going to expand upon that relationship. So moving into the steps over how we're going to solve this is that the first step is that we're going to sort the intervals by their end times. Then we are going to initialize a variable to keep track of the end time of the last interval. Then we are going to initialize a counter for the number of intervals to remove, and we're going to have a for each loop that we will have for each interval in the sorted list of intervals. We're going to do two cases. If the start time of the interval is greater than or equal to the end time of the last interval, we're going to update the end time of the last interval. And then for B, if the start time of the interval is less than the end time of the last interval, we're going to increment the counter And then finally, we're going to return our counter. So to be able to break down the steps over how we're going to write this all from English to regular code, is that the first step, in order to how to sort all of our vectors of a, so we would have an array inside of an array technically for the entire thing, we are going to call upon a sort function that we will create and then use. So we're going to have intervals from begin to intervals at the end. And then we are going to have a series of vectors that will indicate the relationship between the start and the end. So we will have this one here for and A, this one for B, and then inside what we will be doing okay. There we go. Is that we're going to have return A of 1 less than B of 1. So that way we can expand upon the relationship of the beginning and the end. It will be like, for instance, we already know if we were to have 1, 4, 3, and 2, such as in this type of array, we know that 1 and 4 are going to be different as the min and the max. So it's going to be 1, 4. That's how we expand upon our relationship accordingly. And then the next step that we will be doing is then step 2. We're going to initialize the counter, so and a variable to keep track of the end time of the last interval. So for step 2, we are initializing a variable to keep track of the end time of the last interval, and what we'll be doing is that we are going to be doing an int min to start with. And it may be confusing because you think of end as max, but the reason why that we're going to be starting off as int min is, say for example, since we're starting off from absolutely nothing to begin with, we need at least one variable that's going to be greater than what would be provided. And so the reason why that we have int min, it's kind of like saying, for example, if we were to start our given interval with 1, just to give an example, if we were to start our interval at 1, that could be just the entire base that we would have. And if we were to figure out exactly what our maximum will be, we don't know what it will be, but we are starting this off as the maximum value, such as we're setting a baseline, and then eventually in our for loop, what we are going to be doing is that we're going to be updating our last end time to become the maximum value, and it will be further explained in our solution. And then step 3, this is where we initialize our counter. Our counter, it will be int count to remove at 0. And then we're going to head over to step 4, where we're going to create a for each loop accordingly. So for auto and interval for intervals. This is for A. If the current interval at the current index is greater than or equal to the last end time, if we have a given value, then what we'll be doing is that we are going to update last end time to be the next interval value that would be up. So that way, therefore, last end time will be the maximum. Declare last end time to be our maximum. And since we're going to hold this accordingly until we reach the end of the entire intervals array that we have, that means for our counter, if the this would be for B in this case, where if the start time of the interval is less than the end time of the last interval, and we're going to increment the counter, it's kind of like saying, oh, hey, for instance, if we have an interval starting at 1 and we have another, integer we come across, that's the same. It's technically overlapping. So it would be like 1, 1 in that case. And therefore, we will increase our counter and finally, we're going to have our output, which would be step 5. And that's going to be return count to move. We need to increment this accordingly while we are going through our entire for loop, as indicated right over here. Now let me just double check to make sure it's all correct. Count to remove right here. Yes. I'm going to run this to make sure it's all correct. Alright, it passes all the test cases. Let me just clean this up for you folks, just to be sure that we are keeping everything correct and clear as possible. And I'm going to have this in the comment section as well. Alright. Make sure it's right. Pass all the test cases. Okay, now just to give a rundown on everything for our solution, is that the time complexity for our solution is going to be of O n log n, where n is the number of intervals, and this is due to sorting in step by step at the beginning, while the space complexity for our following solution is going to be O of 1, as we only use a constant amount of space to keep track of the last end time and the number of intervals to come to remove. So yes, this was non-overlapping intervals. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the Blind 75 in C++, and today we're working with merge intervals. Now, before we get started, feel free to pause the video to be able to write down the 4 questions we need to do in order to break down the following problem. Again, feel free to pause the video. We first need to ask ourselves for every question what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and then what our output is going to be. So, now to break down the following question that we have, given an array of intervals where intervals I equals start of I, end of I, merge all overlapping intervals and return an array of non-overlapping intervals that cover all the intervals in the input. So we already know what our input is. We're given an array of intervals with start and end. Indices. And we need to merge all the intervals, merge all of the overlapping intervals, and return an array of non-overlapping intervals that cover all the intervals in the input. And so if we were to break down the example 1 and 2, let's say, for instance, we have intervals equal 1, 3, 2, 6, 8, 10, 15, and 18, our expected output that we have is that we need to merge all the overlapping intervals and return an array of non-overlapping intervals. So we have 1, 6, 8, 10, 15, 8, and it looks like from what we have, we're able to merge the rest of the intervals that we have into 15, 8, 8, 10, and then 1 and 6. And it may be confusing to be able to start, but we merge 1 and 3 and 2 and 6 together to make one interval. Since the intervals 1 and 3 and 2 and 6 overlap, we merge them into 1 and 6. Pretty vivid example. Right over here. Just going to put this in the comment section as well. And then we also are able to do the same for intervals 1 and 4, 4 and 5. They come together to become 1 and 5, and it's because 1 and 4 and 4 and 5 are considered overlapping. All right, it's pretty self-explanatory over what we need to do. And so the technique that I will be introducing you folks to is we're going to be doing a sorting approach with an iterative method, where what we will be doing with the data in order to merge all the overlapping intervals is that we will first sort the intervals based on their start times. Then we will iterate over the sorted intervals, merging the overlapping intervals. And iterating means to go through or scan through. That's just a fancy way of putting it. And so just to be able to go over the steps over how we're going to do this is that for step 1, we need to sort the intervals by their start time. In step 2, we need to initialize a new list for the result. And for step 3, we're going to do a for each loop for each interval in the sorted list of intervals. If the result list is empty, or the current interval does not overlap with the last interval in the result, we're going to append the current interval to the result. And then for part B, if the current interval does overlap, we will merge it with the last interval in the result by updating the end of the last interval in the result to be the max end of the last interval in the result and the current interval. Part B may be a little big, but I'll explain more when we write out our code. And then we have, finally, we need to return the result list. So now the way how it's all going to look is that for step 1, we're going to sort everything with our intervals, where we get up here, begin, end, and then we're going to have a list that we're going to create, which will be a vector int. Then we have a list inside of a list, which is why we have vector int, and then we have result. Then we're going to do step 3, which is going to be our for each loop for auto and interval for intervals. We're going to do A and B. If result is empty, or result back 1 is less than interval 0. So that means that we have a maximum that will be less than our minimum interval. In this case, we're going to push the current result that we have inside of our list, so that way we can figure out exactly result.push back interval. We will add the following index of intervals that we have not put inside of our result list. And then else in this part, if it does overlap, we will have result back 1 to be the max result back of the following next interval that we would have, interval 1. And finally, we will return our result. Let's make sure that we have everything right. We sort, we create a list, and then we're going to scan throughout our entire intervals array. And what we will do for everything that has not been added, we will add our interval inside of our result list. For part A, if the result list is empty or the current interval does not overlap with the last interval in the result, we're going to append the interval to the result. That means we're going to put it inside of our result list. And then for B, if the current interval does overlap, we're going to merge it with the last interval in the result. We're going to merge these two together. And then updating the end of the last interval right over here into the result to be the max end of the last interval in the result and the current interval that we would have. So we are just focusing on merging these two together. Then we return a result. Let me just make sure everything's all correct. Let's run this. All right, it passes all the test cases. Let me just clean all this up for you folks. So that way you're able to get a good look and see from the whole result that we will have. I'm going to put this in the comment section as well. Double check. Submit. All right, and it passes all the test cases. So to give a breakdown on the time and space complexity for our solution, the time complexity is going to be O n log n, where n is referring to the number of intervals, and this is because we have to sort the intervals first, which takes O n log n time, and the subsequent merging of overlapping intervals takes linear time, hence the extra n. And then the space complexity is O of n, where n is the number of intervals, and in the worst case scenario, none of the intervals overlap, and the result list will contain all the original intervals. So yes, this was merge intervals in C++. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blind 75 in C++, and today we're working with the insert interval. Now, before we get started, make sure that we have our 4 following questions already set up in place. If you want to follow along, feel free to pause the video. First, we need to ask ourselves exactly what our input is going to be, what data structure / algorithm / technique we need to use, what to do with the data, and what our output is going to be. Again, feel free to pause the video if you are following along to write out the comments for these questions accordingly. So now, when to break down the following problem, you are given an array of non-overlapping intervals where intervals I equals start of I, end of I, represent the start and the end of the ith interval, and the and intervals is sorted in ascending order by start of I. You are also given an interval, new interval equals start and end, that represents the start and end of another interval. Insert the new interval into intervals such that intervals is still sorted in ascending order by start of I, and intervals still does not have any overlapping intervals. And we may need to merge overlapping intervals if necessary and return intervals after the insertion. Okay, so based on the following problem, you're given an array of non-overlapping intervals. That's the start. You can also look at the parameters at the top to be able to see exactly what we are looking for. And then we're also given a new array of intervals to insert in the intervals array. And so it looks like from the following data over exactly what we need to do. We need to insert the new interval into the intervals such that intervals is still sorted in ascending order and they are all the intervals are non-overlapping. All right. And it looks like for our output, we need to return another interval where the numbers are not overlapping each other with the new inserted interval we are given. Okay, and so if we want to break down the following example, say for instance we have intervals equal 1, 3, 6, and 9, and we have a new interval 2 and 5, and our output is 1, 5, 6, and 9. It looks like from the following, since the problem also states that we may need to merge overlapping intervals if necessary, because we need to return the new intervals that don't have any overlapping intervals. So we have an intervals array, and then for our output 1, 5, 6, and 9, these numbers are non-overlapping. So the relationship that we are seeing between the input and the output is that, well, if we are given a new interval, we need to insert that new interval on the inside. So we would have 1, 3, 6, and 9. But since 2 and 5 are overlapping 1 and 3, this is why we merge 1 and 3 with 2 and 5. So we get 1 and 5 accordingly, and then 6 and 9, because all these intervals are non-overlapping and we insert the new interval. Now if we were to look over example 2, we have an array of intervals to start with and a new interval 4 and 8. Well, it looks like 4 and 8 merge within 3, 5, 6, 7, and 8, and 10. So these three different intervals are having 4 and 8 be overlapped inside of them, and we need to merge them accordingly, which is why we get 3 and 10. And so our output would be 1 and 2, 3 and 10, 12 and 16 as non-overlapping intervals. And the explanation is pretty self-explanatory, because the new interval 4 and 8 overlaps 3, 5, 6, 7, 8, 10, which is why we merge 3, 5, 6, 7, 8, 10 to get 3, 10, because we have 4 and 8 overlap these set of intervals. And so the technique for us to be able to solve this problem is going to be an iterative approach, which is a fancy way of saying, hey, we're going to scan throughout the rest of the array, and we're going to make a series of conditions to abide by in order to replicate the behavior for our input and our output. So the steps in order for us to be able to solve this problem is that for step 1, we need to initialize a new list for the result. In step 2, we're going to create a for each loop where we are going to iterate over the list of intervals. And inside of a for each loop, if the current interval does not overlap with the new interval and occurs before it, we will add the current interval to the result. So it would be like, say for example, if we were to have 3, 4, 6, and 9 as just an example. And if it occurs before, and then we have new interval equal 1 and 2, all that together, since it will occur before, we will get the output of 1 and 2, 3 and 4, and then 6 and 9. And then for step 4, we're going to do the same thing, except for it's going to be after. So if the current interval does not overlap with the new interval and it occurs after it, we're going to add the current interval to the result and update the new interval to the current one, since we are scanning throughout our array. Array of intervals. So that would be an example of, say for instance, 3, 4, 6, 9, and then the new interval would be 10 and 12. So we would have the following: 3, 4, 6, 9, and then 10 and 12 accordingly. Then for step 5, in this case, if the current interval overlaps with the new interval, we will merge them into a new interval, much like in the case of example 1. So we would have that's how we do it. So the following example that we have, just want to space this out, and I'll also put this inside of the comment section as well. And then for step 6, what we will do is that we will add the last interval to the result and finally return the result. So to be able to give a breakdown on the following problem that we have, step 1, we need to initialize a new list for a result. So it's going to be a vector inside of a vector for int, and then we have result, given the fact that it'll be like 1 and 3, and then we have a vector that is containing other vectors as well. So here's another vector, and it's a whole vector that we have. That's just how we do it in C++. And then step 2, we're going to create our for each loop. Well, it will be a for auto and interval inside of our intervals array. And then we're going to do steps 3, 4, and 5. Where we're going to have our if statement. Then we'll have our else if statement. Finally, our else statement. Okay, now for step 3, if the current interval does not overlap with the new interval and occurs before it, well, it looks like for the current interval of 1 comes before new interval at that following index. Before, for if the current interval does not overlap the new interval and occurs before it, we will add the current interval to the result. So result dot push back for interval. We're going to put that in there. So that's what we do. And it will be much like in the case of here. Or it could be like another case of okay, actually flipping these examples all together. So we'd have this one, and then we'd have this one, just to visualize. There we go. That's more like it, because it occurs before, and then we have this one where it occurs after. So that totally makes sense. And then we're going to update our following. All right, so then else if, in this statement, we're going to have our new interval, 1, be less than the interval of 0 accordingly. Then for step 4, we will add it. So if the current interval does not overlap the new interval and occurs after it, add the new interval to the result. So it will be result dot push back for the new interval, and then we're going to have a new interval equal interval. And then finally for our else statement, step 5 is if the current interval overlaps with the new interval, we merge, and this is how we're going to merge. We're going to have the new interval 0, indicating for like the lower end, and then for the upper end at the same time. So this will be min. And then we'll also do the same for after. Oh, hold on, give me 1 second. Max of it. That's how we do it. So we're going to have a new interval of 0, and then interval of 0, and then we're going to have the max of the new interval to determine what it will be, or the interval for the max of it at 1, respectively. Make sure that we also put our semicolons already set in place to make sure the syntax already lines up. We're going to do step 6, where we will add the last interval to the result. That would be result dot push back new interval after we have already checked everything and scanned through our rest of our intervals if it all matches up between our conditions. So this would be before, after, and then merge in this case. Again, I'll put all these steps accordingly inside of the comment section. And then finally for step 7, we're going to return our result. For we are creating a list as a result from everything that we have already created. So let me just clean this up for you folks to make sure we have already set everything in place. I'll put step 1, 2, 3, 4, 5, 6, 7. And again, I'll put this in the comment section. All right, also on 0, push back, interval and intervals. Yep. All right, it passes all the test cases. Let me just put this up for you folks so we can explain more about the space and time complexity. Double check. All right, and submit. Okay, now, just to be able to give a breakdown on space and time complexity for our following solution is that our time complexity for our solution is going to be O of n, where n is the number of intervals, and we only iterate over the list of intervals once, while the space complexity is going to be O of n, given the fact that we are storing each interval that we have already visited into our result list, and so that's why in particular it will be O of n, for n is representing the number of intervals. And yes, so this was insert interval. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we're going to go over the blind 75 in C++, and today we're working with a number of islands. Now, before we get started, feel free to pause the video if you want to follow along. We need to, as always, have our 4 questions that we need to ask ourselves in order to break down the problem. We first need to figure out what the input's going to be, what data structure / algorithm / technique we need to use, what to do with the data, and what our output's going to be. So, feel free to pause the video, write out the comments as accordingly if you want to follow along to be able to help break down the problem, and let's continue. So, to break down the problem, given an m times n 2D binary grid, which represents a map of 1s, which represent land, and 0s, which represent water, return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are surrounded by water. Okay, just to give a breakdown on the problem, we already know in particular that we are given a 2D binary grid with 1s and 0s, 1s which represent land, and then 0s which represent water. And it looks like we've got to return the number of islands. It sounds like that we're going to have to create an account at some point to be able to solve this following problem. And so, if we want to go further in depth on the examples that we are given, example 1 has a grid between 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so if we want to highlight this, we got 1s here, 1s there, and they're all adjacent 1s and 1s accordingly. We have 1 island, and our output is going to be 1. Now, if we were to expand on example 2, we have the grid already here, and then we have 1s, so we got 1 island, then we have 1 island over here, then we have another island over here. The rest of them are just 0s, and the output is going to be 3. So the technique for us to be able to use to accomplish this pattern, we're going to use depth first search, where unlike breadth first search, depth first search, and I'll also have a visual to be able to add and explain more. Depth first search focuses on the levels, in particular, starting from the leftmost all the way to the right. So it's going down, then it's moving up from each branch accordingly until all the nodes are accounted for and they're all connected starting from the root. That is the key difference between depth first search and breadth first search accordingly. And so the steps needed to be able to solve the following problem is that to keep in mind over what we're going to do with the data, we're going to overall
we will traverse the grid and perform depth first search for each one cell and increment our counter accordingly. We will create a recursive function called DFS, which we will use to implement depth first search behavior. And so, just to give a breakdown on the steps on how we're going to do this accordingly, is that the first thing that we need to do is that we will we're going to initialize the counter to count the number of islands, and that will be int counter 0. Int counter is equal to 0, and then what we will be doing is that we're going to loop over each cell in the grid, every row and column, which is going to be indication. We're going to have a nested for loop. Then in the third step, what we will be doing, I'm just going to expand this even further, is that eventually we're going to return the island counter. Now, for each of the steps that we have accordingly, step 2 is really just where everything's going to be coming to place. So I'm going to expand upon this step and write some extensive pseudocode to be able to understand exactly how to create and build out our depth first search function, because we're going to be doing a recursive call to be able to create our depth first search function that we're going to call back inside of a for loop. So for each cell in the 2D grid, that means I'm going to put this in parentheses right over here. For each row in the grid and for each column in the grid, since we're counting one by one, we're going to increment our counter by 1 if the character, since we're working with characters, I know it can be confusing initially to start if we're, oh yeah, we have these numbers, they're going to be integers. No, look at the quotations over here. These will be characters, and also in the parameter, we're given characters. If the character is equal to 1, we will increment the counter, and then we will call upon our depth first search function to account for any adjacent islands. And then finally we will return the counter. So step 1, this is how we initialize our counter. It's going to be int count, going to be 0. And then for step 2, accordingly, creating our nested for loop for int I is equal to 0, and then I less than grid dot size I plus plus. Then we will have another for loop for the columns, int j equals 0, and then j is going to be less than grid of I dot size. Then j is also being incremented as well. Then we will have this condition for this part. If the character is equal to 1, so if grid I of j is going to be equal to the character, use single quotations, 1, then we will increment our counter, which will be count dot plus plus, and then we're going to call upon a function we're going to create recursively, depth first search, with the parameters grid, I, and j for a row, since, hey, we have a vector of a grid that we're using accordingly. And finally, for step 3, we will return our count to count for everything. But before we do so, we have this function we need to create called depth first search. So to do that, we are going to create a private function, and we start with void for depth first search. It's a custom function. Then we have a vector of characters kind of like what we have up here. We got a grid. Then we will have and grid to indicate that this is a character, much like, oh hey, a character of grids, and grid. Just like up there. That's cool. Then we have int I, int j for the rows and columns. Now we need to implement the directions of depth first search accordingly. Depth first search is going to have directions up. It's going to, the way we're going to create our depth first search function is the following. Is that the first thing we will need to do, we need to account for edge cases. So 1, if the current cell is out of bounds, or a 0, we will just put in return to indicate nothing, and it won't be in the counter. That will just how we will label. I'm just going to tab this over here, tab that here, and then we're going to mark the current cell as 0 to initialize our current position. Then what we will be doing is that we are going to recursively perform depth first search for neighboring cells up, down, left, right. So this is what we will be doing for our depth first search function that we will have. Just put this right here, put it side by side to help you folks out. And I'm also going to put this in the comment section as well to help. So first part, this is the edge case that we'll have. If I is less than 0, because it needs to be in the bounds, or I is greater than or equal to the grid dot size, since I represents the rows, or j is less than 0, or j is greater than or equal to grid of 0 size, or the grid of I and j accordingly is equal to 0. We're just going to put in return to indicate that nothing is there, and then we're going to initialize our grid position at I and j, and it's going to update accordingly while we are going through our for loop, and then call recursively in our depth first search function. Now for the directions. After I make this equal to the character of 0. Now for our directions. Up, down, left, and right. Left, right, recursive call. So this will be up, depth first search, as indicated right up here. We have a grid, I minus 1, and then j. No, actually, plus 1, up, no, hold on, here we go. So up, down, left, and right for our following. Let me just put this right here. This will be up, search, grid, I, j minus 1, down, DFS, grid, I plus 1, right, j, and then left, DFS, grid, I minus 1, j. Up, down, left, and right. Up, down, left, right. Okay. So this should be right, and accordingly what we have, I'm just going to clean this up so you folks can be able to see thoroughly. Actually, I'll put this right here for the sake of it. And here we go. I'm going to put our notes all the way up here. Here we go. Let me just double check. I, row, column, grid of I. All right. Let's run this. There's an error. Don't forget the semicolon. All right, it passes all the test cases. And submit. All right, and it works pretty well. Okay, so now to just give a rundown in terms of our space and time complexity for the following solution, is that the time complexity for this algorithm is going to be O of m times n, where m is representing the number of rows and n is representing the number of columns in the grid. And in the worst case, we might need to visit every single cell in the grid once if the grid is filled with land. And then the space complexity for our algorithm is O of m times n, where n, in the worst case, where the grid map is filled with lands, where depth first search just goes by the number of rows and columns multiplied together, and just continues in a depth first search type of recursion. So yes, this was Number of Islands. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blind 75 in C++, and today we're working with a number of connected components in an undirected graph. Now, if you're following along, feel free to pause the video to write out the comments that we need to do for whenever we are breaking down a problem. We always need to ask ourselves 4 questions. What our input's going to be, what data structure / algorithm / technique we need to use, what to do with the data, and what our output's going to be. Again, feel free to pause the video to write out the comments if you're following along. We will start breaking down the problem. So, you have a graph of n nodes. You are given an integer n and an array edges where edges I equals a of I, b of I. It indicates that there is an edge between a of I and b of I in the graph. Return the number of connected components in the graph. So we have n equals 5 and edges 0, 1, 1, 2, 3, and 4 with an output of 2. In this example, we have one connected component and another connected component. If we were to go over example 2, we have, looks like 1, 2, 3, 4, 5 nodes, and we are given a, looks like, an array of edges accordingly, and they're all connected just based on the nodes and their type. And since we have a vector inside of a vector in this case for each one, and they're all interconnected, the output is going to be 1. So looks like from our input it will be a number of nodes in the graph, which is going to be n, and a list of edges representing the connections between nodes. And it looks like our output is going to be the count of connected components in the graph. And it looks like, since we were focusing on connectivity in this case, and we were dealing with a graph problem, a thing to note in trees, popular methods to be able to solve the following solution would be depth first search or breadth first search. And depth first search would be ideal for a solution since we are focusing on connectivity of the nodes. And the differences between depth first search and breadth first search is that depth first search focuses on the connectivity starting at the root of a given tree or graph, and then goes to the leftmost type of node on a downward, hence depth in the name, and then does the same thing for the right branches accordingly, starting from the leftmost branch, while breadth first search, on the other hand, focuses on the nodes per level. So for instance, on breadth first search, we have one level, and then it just counts the nodes from the left to the right accordingly. unlike depth first search. And since we're focusing connectivity, depth first search would be the technique to use. Count the number of connected components. So we will use depth first search to find the connectivity of the nodes and count the number of connected components. And what we will do with the data is that by principle we will create an adjacency list to represent the graph. Then, starting from each unvisited node, we will perform depth first search to explore all connected nodes and mark them as visited. And so the steps for us to be able to go over this entire thing, and I'll also have expanded pseudocode as well, is that for step 1, we're going to initialize an adjacency list to represent the graph. In step 2, we will create a variable to store the count of connected components. Step 3, we will create the adjacency list to represent the graph we are given. In step 4, we're going to perform depth first search to count the number of connected components. Step 5 will then return the count of connected components. Now, to expand on each of the steps that we will do is that after we initialize an adjacency list to represent the graph, we're going to create a variable to store the count. The third part is really going to be we will loop over to create the adjacency list to represent the graph we are given. We need to loop over our given edges and loop over each edge in the list of edges. And then we'll add the 2 nodes of the edge to each other's adjacency list. Then for step 4, where we perform depth first search, is that we're going to loop over each node from 0 to n minus 1. And then if the current node is unvisited, we perform depth first search to explore the connected component, and then we're going to mark the current node as visited, and then 2, we're going to explore all neighbors of the current node using depth first search. And the depth first search function accordingly will be at the current node, we will mark the current node as visited, and then we're going to recursively perform depth first search on all unvisited neighbors of the current node. And finally, what we will do is that we will increment the count by 1 after completing the depth first search for a connected component. Alright, so that's how we will go about this accordingly. Now, just going about this step by step. Actually, for our depth first search, since it will be called upon recursively, I'm just going to put this right here. Unvisited, yeah. So the depth for search function will have these two components: mark the current node as visited, and recursively perform depth for search on all unvisited neighbors of the current node. So to break down over exactly what we're going to do, since we're doing a recursive call, we're going to have two different functions for a solution. Let me just actually put output right over here for sake of clarity. Step 1, step 2, step 3, step 4, step 5, and then we're going to perform our depth for search function, which will be located right there. So step 1, to be able to do, is we will have our vector int adjacency list based on n size, which will account for all of the nodes that we have visited. And then we are going to have a count for all the connected components as indicated by step 2. Then for step 3, let's put it right here, we're going to loop over the edges to be able to create our adjacency list. So for constant auto at edges int u, this will be representing edge 0, and then int v representing edge 1. The next one, since they're all connected, this is how we add the adjacency list. We'll have adjacency list of u dot push back of v. Then we'll do the same thing, but since they are connected, we just flip over the v and the u accordingly. And for step 4, we're going to perform depth for search, since we have already created our adjacency list. And the way we do that is that we're going to create a vector for everything that hasn't been visited, and we're going to set it to false, indicating we haven't visited yet. This is how we initialize. And then what we will do is that we are going to loop over our edges. Int I is equal to 0, and I is less than n, where n is referring to the number of nodes that we've already visited. Then I is also being incremented as well. And so for everything that has been visited, if we haven't visited the current index, what we will do is that we're going to perform depth for search accordingly. For A, is that we're going to have depth for search of I, adjacency list, and visited. Just want to be sure I got the spell right. And then we are going to increment our count, since the second step is we are going to explore all the neighbors using depth for search. So we're going to call upon our depth for search function for everything that hasn't been visited. We're going to call upon depth for search to explore connectivity. Call upon depth for search to explore connectivity. Then we increment our count. We increment our count by 1 after completing depth for search for a connected component. Again, if it hasn't been visited, and we'll expand more in the def for search function as well. So increment our count, and after our count, we're going to return a result, so we will return count. Then we will have def for search, so we have private, void. Ooh, right. Def for search int node, constant vector, of int, and adjacency list, vector, boolean, and visited. Just want to be sure I got that right. Then we're going to mark the current node as visited, as indicated by our notes up here. So we do that with visited node is equal to true, since we're dealing with a true or false statement. And then we are going to do for a of 2 in this case, where we are going to recursively perform def for search. So for int neighbor, for every single neighbor, list of node, if visited neighbor, we're going to call upon def for search to be able to have our neighbor, adjacency list, and then visited. There we go. All 3 accordingly. Let me just clean this up prior to submitting, then checking to see if we have anything already set up in place. Yep, that's what we do. Let me just run this, double check, misspelled visited. There we go. It passes all the test cases. Submit. Alright, and now just to give a breakdown on the space and time complexity for a following solution is that the time complexity for the solution is going to be O of n plus m, where n is the number of nodes and m is the number of edges in the graph. And meanwhile, the space complexity is going to be O of n, where n is the number of nodes, as we use additional space for the adjacency list and the visited array. So yes, this was number of connected components in an undirected graph. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blind 75 in C++, and today we're working with longest consecutive sequence. Now, before we get started, feel free to pause the video in order to actually fill out the comments necessary to be able to solve this problem. For when starting this problem, we are usually going to be asking ourselves 4 different questions. We first need to ask ourselves what the input's going to be, what data structure / algorithm / technique we need to use, what to do with the data, and then finally what our output's going to be. So now, breaking down the problem, given an unsorted array of integers nums, return the length of the longest consecutive element sequence. You must write an algorithm that runs O(n) time. Okay, so to be able to give a breakdown over exactly what we need to do for the following, the first thing that comes to mind is that, well, for one, our given input is that we are given a list of nums, especially when looking at the example, and the expected output is to return the length of the longest consecutive element sequence. So if we were investigating this, the longest consecutive elements inside of the whole thing, depending on how it's jumbled up at the same time, so we have 1, 2, 3, and 4 are the longest consecutive, so therefore it would be 4. And then since we have all these numbers already jumbled up together, but we still have an output of 9, we have the following longest consecutive sequence being 9, since it starts from 0 and goes all the way up to 8 accordingly. And the technique that we will be using for this actually
is that we will be hashing. Now, hashing is a way where we are able to actually keep track of the length of a given sequence accordingly, where we are able to break up our given data and keep track of each part accordingly. So what we will do, namely, is that we will insert all numbers into a hash set for fast lookup, and then iterate through each number and check if it is the first number of a sequence, then count the longest sequence it can form. Alright. Now, for us to be able to go over the steps on how to replicate this type of hashing behavior, is that the first step we need to do is that, one, we need to create a hash set and add all numbers to it. Then we need to initialize a variable to track the max length of a sequence. Then we will loop through each number in the array, since we were dealing with arrays, and then we're going to check if it is the first number of a sequence. Num -1 doesn't exist in the hash set, and then if it is, then count the length of the sequence it can form and update the max length if necessary. Finally, we return the max length. Alright, so now just to give an update over how step by step we're going to create this is that I'm going to put this up here for sake of cleaning. Is that step 1? We create a hash set, so it's going to be an unordered set of integers that we have, where our set is going to have the nums array from the start all the way to the end. And then we're going to do step 2, where we initialize the max length 0. Then we do step 3, where we are going to be looping through our nums array. So in this case, it's going to be for each loop, so it's going to be a num of nums. Then check for the first number sequence, A, over here. If it's not in the set, count. If it's not in the set, num -1, then we start checking. So we are going to have our current length set to 1. It is the first number of a sequence, and then while num +1 exists in the hash set, while set.count num +1 exists in the hash set, we're going to increment our num count, and then we're going to update the current length as well. And then we will be updating our max length if necessary. So max length is equal to max of the max length, current length. And finally, we will return right here. Just double check on this. Okay. There we go. That's more like it. And then we have return max length. That'll be step 4. Let's just double check to be sure everything is already correct. Let's run this. Alright, pass all the test cases and submit. Okay, so just give a rundown and breakdown of our following space and time complexity for the following is that the time complexity is O of n, where n is referring to the number of elements in the input array. The space complexity is O of n, which is used to store the elements in the set. So yes, this was longest consecutive sequence. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blind 75 in C++, and today we're working with the problem merge to sorted lists. Now, before we get started, feel free to pause the video if need be. For whenever we are solving these types of problems, we always need to ask ourselves these 4 types of questions. And if you're following along, feel free to pause the video to take some time to write out these comments. For whenever we are breaking down the problem, we need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, to give a breakdown of the problem, you are given the heads of 2 sorted linked lists, list 1 and list 2. Already self-explanatory. You can also look at the parameters up here to justify. Merge the 2 lists in one sorted list. So, we got to do that. The list should be made by splicing together the nodes of the first 2 lists. And then return the head of the merged linked list. Okay, well, it looks like we got to merge the 2 lists in one sorted list. And we found a way, literally just from the question, to be able to break it down based on keywords and knowing how to organize it. So it looks like, in particular, that we are just merging all of the linked lists together, like we have list 1, list 2, all of them being sorted and merged accordingly. If we have an empty list, we just have an empty list return. And then if we have an empty list and 0, so we have 0 right here, and the numbers can go from -100 to 100 in value for each node, and the number of nodes in both lists is in the range of 0 and 50, the node value. Interesting. And then we have both list 1 and list 2 are sorted in non-decreasing order. Alright, so we already have that. So luckily, what we will do, because of how easy it was to be able to dissect the problem, is that we're going to use merge algorithm of merge sort, where, as the name explains, what we're doing is that we will be creating an algorithm to merge both of the linked lists accordingly, and then we will be sorting them. Ultimately, we can sort them first and merge them all together. Well, since we already have 2 sorted linked lists to begin with. And what we will do is that we're just going to check while we are scanning through them. So the steps for us to be able to operate on this are the following. Step 1, we need to initialize a new head and current pointer. And step 2, while both list 1 and list 2 are not null, if list 1's value is less than list 2's value, we will add list 1's node to the current list and move list 1 forward. Otherwise, we will add list 2's node to the current list and move list 2 forward. Then, while we are doing this inside the while loop, we're going to move the current pointer forward after adding the node, since everything is already sorted, and that helps us a lot. And after exiting the loop, if there are any remaining nodes in either list 1 or list 2, we're going to add them to the current list. And 5, we're going to return the new list from the head. Okay, just to give a breakdown over exactly how we're going to go about this, just going to write this out accordingly. Step 1, step 2, step 3, step 4, step 5. I'm just going to clean up all this for you folks.
And step one, the way how it's going to look about is that we are going to create our node dummy equal the new list node -1. The reason why is that this is just how we initialize it. And list node current equals dummy. Then list 2, we're going to create a while loop while list 1 doesn't equal null, and list 2 doesn't equal null. This would be A and then B. So A will be if list 1's value is less than list 2's value. If list 1 value is less than list 2 value, we're going to add list 1's node to the current list. So current next will be list 1 and move list 1 forward. So list 1 is going to be list 1 of next. And the reason why we do this, we can even look up here and leverage off of the list node data structure that we are also given to, which is why we have next to begin with. And then we're just utilizing that along the way. And then else, in the other case, we're just going to do the same thing for 2. Basically, current next list 2. And then list 2 is equal to list 2 next. We add the current node to list 2 based on this condition that we have up here of list 1's value being less than list 2's value, and if not, then we are going to add list 2's value to the current list. And then for step 3, inside of our while loop, we're going to move the current pointer forward and add the next node. So current is equal to current next. Just want to be sure I got this. Okay. It should be in here. Just want to be sure if we have it all set up in place. Yep, it's in the while loop. And then for step 4, after exiting the loop, if there are any nodes remaining in list 1 or 2, we're going to add them to the current list. So if list 1 is not null, we're just checking for any outliers. We're going to move current next because we assume in the while loop we have scanned for everything. And this is just for safe measure. The current next equals list 1. And then else if list 2 doesn't equal null, then we're going to have current next list 2. And then finally, we are going to return the head of our dummy. So return dummy of next, because we stored everything inside the head of our dummy linked list. So let me just double check to see if we have everything that's right. If else, yes, we do. Okay. Let's just double check. All right, it passes all the test cases and submitting. Okay, so now just to give a rundown on the space and time complexity for our following solution is that the time complexity is O of n plus m, where n and m are the lengths of the two lists. And this is because in the worst case scenario, we have to visit every node in both lists once when merging. While the space complexity is O of 1 because we only initialize a fixed number of pointers and do not use any auxiliary space that scales with the size of the input. And so yes, this was merged two sorted lists. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blind 75 in C++, and today we're working with merge case sorted list. Now, before we get started, feel free to pause the video if you're following along. For whenever we are breaking down any problem, we always need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, Feel free to pause the video if you're following along to write out the comments. And just breaking down the problem right now, you are given an array of k linked lists called lists. Each linked list is sorted in ascending order. Alright, we know exactly what our input's going to be. Merge all the linked lists into one sorted linked list and return it. And we know what to do with the data. We need to merge all the linked lists into one sorted linked list. And return a merged linked list. We will need to create a dummy linked list to return from the head. Few indications. And so the technique for us to be able to replicate this problem, just looking over the example, again, it's pretty self-explanatory. We're given a list of different linked lists, and the k is going to be arbitrary. So we have 1, 4, 5, 1, 3, 4, 2, and 6, all separated by commas. They're all different linked lists, and then we need to merge them all together, and then finally have this output. So the technique that we're going to be doing is going to be a priority queue with a merging algorithm. So that means, in particular, what we will do is that we will, for one, we would need to create a structure to compare the values of each node from one list to another. That's just a key indication over what we need to do. For queues, in our case, what we will be doing for this data structure, queues in general operate on the principle of a last in, first out situation, much like in the case of a grocery cart line, where people are going in throughout the line and then they happen to appear out of the line. In some retrospect, that's how queues operate. And so the steps that we would need in order for us to be able to go through are the following. One, we're going to create a Boolean function called compare to compare the values of each linked list, labeled list 1 and list 2. Second, we're going to initialize a priority queue that orders the nodes by their values. The third step, and then for each list in the input, if the list is not empty, we will add our first node to the queue. Then the fourth, we will initialize a new head and current pointer for us to return. Then we will scan the queue, and while the queue is not empty, we are going to move the current pointer forward after adding the node, and then we will return the new list from the head, which will be called dummy. So the way how this is going to work out accordingly are the following steps. Step 1, step 2, step 3, step 4, step 5, step 6, step 7. A thing to note, since we're going to be comparing the values, we're going to create a separate function all the way at the top, and we're going to start comparing each of the values accordingly. So the way how it will look is that this is how we create a new function that will be called later. We have a structure called compare, and what it's going to be is that it's going to be a Boolean function, or really just an operator, that will incorporate the parameters of a list node, indicating for list 1, and then list node for list 2. And then what we will be doing is that we will return a comparison between the list 1's value, if it's greater than list 2's value. That will be in the case of if we have, for instance, list 1's value being greater than the other. So if we have 5, we're going to place this 5 over here. That's what we need to do in the very first step. And then we're going to call this operator later on throughout the rest of our structure that we're going to create for steps 2 through 7. So that means for step 2, we are going to be creating a priority queue, which will look like this. It's going to incorporate a list node. Then it's going to have the vector of the other list node. And we're going to call upon compare our structure at the top. Oh yes, also another thing. Don't forget this. Hang on. Let me just double check. So it's right here. Just want to be sure I got all the comments right. Okay. It's supposed to be right here when having the new structure. So then, let me just double check. Yes, we have a priority queue. We're going to call that PQ. And for step 3, what we will do is that we're going to have a for each loop. I don't know why it's not letting out, but we'll check to see. This will be PQ for priority queue. Then we will have our for each loop in step 3. For each list in the input, we're going to put it inside of a priority queue. So we're going to have auto list of lists indicated by the parameter. Up here, lists. And then we are going to, I'm just going to move each of these steps away to make it easier on you folks. Just give it there for reference. And then step 7 is going to be our return. And then just put it up here, and we'll just go side by side accordingly so it's easier to see. So then in our for each loop for step 3 is that if we have a list indicating that it's, we have elements in our list, we're going to put that inside of our queue. So it's going to PQ push for our list, which will be called. Then for step 4, after we have added in our priority queue, we're going to create a dummy list node, which will be the linked list that we'll return. So new list node, this is how we initialize it, -1. Then we will have a list node for the current, be the dummy, and the current list node is going to be the one we're going to manipulate throughout 5 and 6, finally returning the dummy, because the dummy is technically the head in this case. So what we'll be doing is that while the queue, PQ, is not empty, it's calling upon the empty function from the STL library for queues, and then PQ, we're going to pop the smallest node from the queue, which will be a list node for a temp. We're just going to label this as top. And then what we will do is that PQ pop. So we get the very top of it. And that will be our temp that we have. So current next. The reason why we do current next is to label out each node accordingly prior to calling our head. So if we were to have PQ pop, we can literally just do the same thing up here and do it accordingly. We just happen to put the list node for temp and call it for pop. But we're just doing it for the sake of clarity. And looks like for step 5, we're going to remove the current pointer. Then the next part, what we will have to do is that we have an edge case inside of our while loop. We still have more nodes to push in after we pop the queue. This would be A. So just want to clarify in this part. We will also push that inside of our queue. if, so it will be if temp for the next following nodes, pq push temp next. And then what we will do is that we will also get the following nodes after. And continue the while loop. So that will be part B. So we are going to set the next current, we're going to set the next node after the current node accordingly and still go through the while loop until we finally have finished scanning throughout the rest of our queue. And finally, what we will do, this will be B, not step 6. Apologies on that. And then this will be step 6. There we go. Then finally, we will return the head, so dummy, for next accordingly. And then B, we're going to move the current pointer after adding the node. There we go. That's more like it. All right, so just to give a rundown, what we're doing is that for step 1, for the solution, is that we are creating a structure called compare, where we're getting the values accordingly to sort all of our following elements. And once we have already done so, we're going to initialize a priority queue, where once we scan our list, after we compare, we call upon compare for our priority queue. Our priority queue is going to push all the following values while comparing them as well into the queue. And then what we will do is that we're going to create a new list as a result from everything that we have already set inside of our priority queue, and then finally return our dummy. So it's technically 3 parts. 1, we have to create a structure called compare that will compare the following values between the previous list and the next list based on their value. And once we have already sorted, then what we're going to do is that we're going to put that sorted, we're going to call upon our sorted function from our priority queue, and we're going to sort all of our list for each element in our lists, linked lists that we are already given, and then push inside the queue. And after we have done so, we're going to scan the entire rest of the queue from the top all the way to each node accordingly, and finally return our new linked list, which is the merged linked list of everything that we have already scanned. So let me just run this just to double check. All right, and don't forget your semicolons. All right, it passes all the test cases. All right, and now just to give a rundown and breakdown of our space and time complexity for the following solution is that our time complexity is O of n log k, where n is the total number of nodes in all linked lists, and k is the number of linked lists. And this is because we need to traverse all the nodes of n, and each insert operation in a priority queue takes log k time. Meanwhile, our space complexity for the solution is O of k, because at any time the maximum size of the priority queue is k, since we only push the head of each linked list into the queue. And so yes, this was merge case sorted lists. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blind 75 in C++, and so before we get started, before breaking down any other question, we always ask ourselves these 4 questions. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output is going to be. So, to give a breakdown on the whole question that we have accordingly, so we are given head, the head of a linked list. Determine if the linked list has a cycle in it. Very self-explanatory. So, for input, we are given a linked list represented by a head node, and it looks like, as we dive further more, there is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, position is used to denote the index of the node that tail's next pointer is connected to. Note that pos is not passed as a parameter. So return true if there is a cycle in the linked list. Otherwise, false. All right. So we will detect a cycle in the linked list where tail is connecting. All right. There's a cycle in the linked list where tail connects on the first node, 0 indexed. Okay. Here, position 0, 1. Here. Okay, so if we look at the following array that we have at our given head, 3, 2, 0, and -4 at position 1, and since arrays by principle also operate at 1, and the end node would also mean at this position at 2, this is why we have position 1 and then 2 connecting with -4. Okay. And then we're also given the input, for example, 2 of head, 1 of 2, and then position 0. And there is a cycle in the linked list where the tail is connected to the 0 node. Got it. Because it's all 0 index. So 1, 2 makes sense. But then we have position -1. We only have a 0. We don't have -1. And there is no cycle in the linked list. Okay. So the technique that we're going to be using is going to be called the Floyd cycle finding algorithm, the tortoise and the hare algorithm, which allows us to detect cycles in linked lists. So it's a pretty straightforward type of algorithm to be able to go about, and it's just really taken into 2 steps. So step 1, what we need to do is that we need to initialize 2 pointers, slow and fast, both pointing to the head node. Then, in the second step, we need to start a loop where the fast node and the node after fast are not null, assuming we have a linked list. And then what we will be doing is that for first part, we're going to be moving the slow pointer 1 step forward. Then for the next part, we're going to move the fast pointer 2 steps forward. And then if the fast pointer reaches the end of the linked list, it could also be considered null, and that could be edge case where we have an empty linked list. Also considered for having an empty linked list. Return false since there is no cycle. And then if the slow pointer and the fast pointer meet, EX, they are at the same node, return true, as there is a cycle in the linked list. And finally, what we do by default, assuming we don't have a linked list to begin with, we return false since no cycle. Okay, so following steps: step 1, step 2. Let me just move this out of the way for you folks. Okay, so first step, we're going to make our fast and slow heads for our list nodes. So list node slow head, and then list node fast for head. We're creating our 2 pointers, and then we're creating our loop while fast doesn't equal null.
and fast next value doesn't equal null. A, B, C, D. Slow equals slow next. And B, we're gonna have fast equal fast next, next, the one after, and then in the case where the fast pointer is null, we return false. Oh. Then in the case where fast and slow meet, if slow equals fast, we're going to return true, and then by default we will return false. So just double checking to see if it's all right and all correct. Slow, head, head, yep. Let's just run this. Alright, passes all the test cases and submitting. Okay, so just to give a breakdown on the space and time complexity for our following solution is our time complexity is going to be O of n, where n is the number of nodes in the linked list, and in the worst case scenario, the fast pointer will traverse the entire linked list before reaching the end of the or meeting the slow pointer, and meanwhile, the space complexity is going to be O of 1, where we only use a constant amount of extra space for the two pointers, regardless of the size of the linked list. And so yes, this was detect cycle in a linked list. Thanks again for taking the time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye.
Hello everyone, today we're going to go over the Blind 75 in C++, and today we're working with Palindromic Substrings. Now, before we get started, feel free to pause the video, since we are breaking down the question accordingly. We need to ask ourselves these 4 questions. If you're following along, again, feel free to pause the video to write out the comments that we have. For every time we see one of these questions, we need to ask ourselves these 4 questions. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally, what our output's going to be. So now, breaking down the problem. Given a string S, return the number of palindromic substrings in it. A string is a palindrome when it reads the same backward as forwards. A substring is a contingent subsequence of characters within the string. So, to be able to give a breakdown on the following examples that we have, like say for example that we have A, B, C, and if we were to have the output of 3, we're given 3 palindromic substrings of A, B, and C, since it reads the same forwards and backwards. That's what a palindrome is by nature, and we have to figure out how many combinations there are. So it looks like we need to return the number of combinations for palindromes with our given string, and here we are given a string S for our input. And the technique that I will be introducing you folks to actually going through on how to break down for the following string is going to be dynamic programming, which is great for reading data both forwards and backwards. And the steps for us to be able to accomplish the following task are going to be the following. Steps 1. What we're going to do is that first we need to initialize the string length and the matrix that will have the string length on the inside to check to see if there is a palindrome, and then if so, it will be true, such as like having A, B, C. So we need to divide up accordingly based on our following string. And then the second step, we're going to create a count as well. Then we're going to iterate through our string S. Most likely it's going to be a for loop. And then for the first part, we're going to iterate backwards. And we're going to do this by the following. We will set dp we will set our given array to be true, indicating we have one string, one palindrome substring. Then the next part, we're going to increment our count since we're moving up. We're going to increment our count to indicate for the number of our substrings that we have. Then we are going to iterate forward. And then for this part, we will check to see if the character at index and the current index is the same as the character current forward index is the same as the character in the backwards index. And in this case for dynamic programming, there is a strong chance, since looking at data both forwards and backwards, we will use a nested for loop. That's just a probability, just something to keep in mind. I will explain more when we are writing out more of our solution. And then the second step is that we're going to check the length of the substring and if the characters at the same substring and also we're going to check the length of the substring if the characters at the same substring with if the characters are the same substring with the length of the substring is 2, then it will be a palindrome. And finally, we're going to return our count. So now just to clean up everything and then showcase you folks exactly how we're going to write this out in our 4 steps. So we have step 1, step 2, step 3, step 4. Here we go. So int n is going to be s.length, and then we're going to have vector bool, vector boolean to be able to check to see if we have a palindrome, and we're going to initialize this as dp. So then our parameters for it are going to have a vector with a boolean to indicate it's false, and this is just how we initialize if we have any type of this is how we're going to check to see in particular if we are going to have a following palindrome, and this is just how we initialize it. Then we're going to initialize our count, and then we're going to iterate forward by actually in the palindrome sequence we look at the data backwards and forwards. So in this case, since we are going to be iterating backwards to begin with and then forward, our for loop is going to look unique. So we're going to treat it like I, but instead it's going to be n minus 1 since starting from the very last element within our given string. And I is going to be greater than or equal to 0 since we're iterating from the back, and then I is going to be decremented. Then what we will do is that we're going to set our current index to true. So dp of I, so let me just put this as 1. And right here, this is how we initialize further, and then we're going to increment our count. Then we will continue inside of our for loop, and this time we're going to iterate forward, so it's going to be b. And the way we do that is that we're going to have int j is going to be I plus 1, since we want a palindrome. J is going to be less than n, where n is referring to our length that we initialized up here. You can even have the for loop as well, s.length, but for the sake of clarity, we just put n. and then j is being incremented forward. Then we are checking for 1 and then 2. So we're going to follow the guidelines. We will check if the character at the current forward index is the same as the character at the backward index, and the way we do that is that if s of I, the current index, and is equal to s of j at the forward index, and we subtract the displacement from the following, set it equal to 1, and j minus I is equal to 1, indicating just the space that's in between. After we have iterated forward and backward, that we have this number. We are then going to call upon a vector to be able to check to see if it is a palindrome, and then add it to our count. So we have I plus 1, and then j minus 1, because if we're incrementing it, this is at the point where it will be backwards, and then this will be forwards as well. But we are checking to see when they finally sync up to each other, because we're checking the length of substring. We are checking to see if the character at the current forward index is the same as the character in the backward index, and we're trying to see in particular when they meet up. So this is why in particular that we have these two components for in our DP vector, so to speak. And moving forward, so DP of I and j is going to be true. Therefore, we're going to increment our count, because we need to check to see if it is a valid palindrome. And then finally, we are going to return our count. Oh yeah, also, this was also part of step 2 at the same time. So we're going to check the length of the substring and 2. Sorry for the confusion over here. So that is how we will set this up. Let me just double check. Alright, passes all the test cases. Alright, and it works pretty efficiently. So to be able to give a rundown and breakdown of our space and time complexity for our following solution is that, given the fact we are using a nested for loop, the time complexity for our solution is going to be O of n squared, where n is the length of the substring s, and this is because we fill the Boolean matrix of the dynamic program of dp based on size n times n, and each cell requires constant time to compute based on the previous results. While meanwhile, the space complexity is going to be a O of n squared, as we use a Boolean matrix of size n times n to store the results of the subproblems. And yes, this was Palindromic Substrings. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the Blind 75 in C++, and today we're working with longest common subsequence. Now, before we get started, feel free to pause the video or follow along accordingly. For whenever we are breaking down these questions, we need to ask ourselves these 4 questions: what the input is going to be, what data structure / algorithm / technique to use, what to do with the data, and finally, what our output is going to be. So let's just break it down. Alright, so now just break down the problem. Given 2 strings, text 1 and text 2, return the length of their longest common subsequence. If there's no common subsequence, return 0. Alright, so we already know what our input and output is. This is our output. If there's no common subsequence, return 0. And remember, we're given 2 strings, text 1 and text 2, right here. And we need to return the length of the longest common subsequence. So that's the first one, return the length of their longest common subsequence. And the technique that we'll be using for this following solution, if we're going over the examples, namely, what we're trying to do is that we're trying to find the longest common subsequence between the 2 patterns of 2 different texts when we're scanning both of them accordingly. And the technique we're going to use is dynamic programming. To scan both text
1 and 2 using a dynamic programming table to check for character and size of our text strings. And the steps for us to be able to go about this are for the following. So step 1, we're going to initialize a DP table with the size of text 1 dot size plus 1 times text 2 dot size plus 1 and when we do so, this is how we create our table. Then what we will do is that for step 2, we're going to loop through each character in both strings. And then for step 3, if the current characters in both strings are the same, the value of the current cell is 1 plus the value of the cell diagonally of the table, both above and to the left of it. And for step 4, if otherwise, if they are different, the value of the current cell is the maximum between the cell to the left and the cell above in our dynamic programming table. Finally, for step 5, we're going to return the value in the bottom right corner of the dynamic programming table we created to show the longest common subsequence. And I'll also have a visual as well for the dynamic programming table while we are constructing this whole behavior. Now, just to clean up everything else and just go straight into the code over how it will look like. So I'm just going to write the steps, just 5 steps accordingly. Step 1, step 2, step 3, step 4, step 5. Let's just get after this. So first things first, we're going to create our table. This is how we do so. We're going to do a vector int, dynamic programming, text 1 dot size plus 1, and then we're going to have a vector of int measures representing the character size for each strings, text 2 dot size plus 1. And now we're going to loop through each of them. So the way we do this is that we're going to have 2 nested for loops. Int I is going to be 1, and then I is less than or equal to text 1 size, I plus plus. Then we're going to do another nested for loop for our following. Instead, it's going to be j is equal to 1. This is representing text 2, less than or equal to text 2 dot size j plus plus. Then we will do steps 3 and 4 on the inside of it for if else statement. If. And finally for step 4, that's going to be our else. So step 3, if the current value in both strings are the same. So if they are the same, we're going to have text I minus 1 equal text 2 j minus 1, and then dynamic programming of I and j is going to be equal to the dynamic programming array if they are the same. So we're going to subtract from 1 over here, and then j minus 1, since we're scanning both, plus 1, make sure that they're the same. Then we increment. And then if they are different, this is how it's going to look. dp of I and j, we're scanning them. We're just going to get the max value between them. So I minus 1, j, then dp I and j minus 1. And finally, we're going to return the value at the bottom right corner of the dynamic programming table. So we're going to do this return dynamic programming text 1 dot size for the following, and then we're going to have text 2 dot size for the next following as well. So let me just make sure everything is already lined up and it's correct. Text 1 size, text 1, text 1, text 2. Alright, let me just double check. Alright, we got a syntax error over here. I forgot the semicolon. Small things like that. And I apologize for this as well. Text 1. There we go, passes all the test cases, and we submit. Okay, and now just give a rundown on the space and time complexity for our following solution. Is that the time complexity for our solution is going to be O of m times, it's going to be O of m and, it's going to be O of m and n, where m is the length of the first string and n is the length of the second string. This is because we fill up our dynamic programming table of size m times n, and the space complexity for our following is also going to be O of m times n for the same reason. And yeah, so this was Long's common subsequence. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to be going over the blind 75 in C++, and today we're working with the problem minimum window substring. Now, before we get started, before we break down every single problem, make sure we have these 4 questions already laid out in order to us to be able to help dissect and break down the problem. We first need to figure out exactly what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output is going to be. Again, feel free to pause the video if you're following along to be able to write out these comments accordingly, and we're going to go through step by step on how to solve this problem. So, breaking down the question, given 2 strings s and t of lengths m and n respectively, so we already know what our input is, return the minimum window substring of s such that every character in t, including duplicates, is included in the window. Okay. If there is no such substring, return an empty string. Okay, so we know our input and our output, and if we were to go about based on the example, so it looks like we have this entire string s and this string at t, and we notice that the output is going to be b, a, and c, where we can find that over here. So this substring has all the characters from this string alone, and it even says in the example, the minimum window substring b, a, and c includes a, b, and c from string t. And we can probably do the same thing for a and a. The output's a, the entire string is s, is the minimum window, and then if the input of a and then t, in this edge case, both a's from t must be included in the window, since the largest window of s only has one a, and we return an empty string. Okay, so those are some things to be able to keep in mind. Now, mind you, since we are dealing with 2 strings, in particular, the technique that we'll be doing is going to be the sliding window technique. I'll have a visual on the side to be able to help illustrate the idea that we're trying to construct for the solution. With the sliding window technique, we will create 2 maps to keep track of the frequencies of our characters, including duplicates,
And maps, basically the best way of visualizing them is that they have a key value pair type of relationship where maps are like lockers in particular and keys. There's a specific data element that we keep track of in order to actually access another data type. So that's the scope really of how maps are seen visually. I'm just giving a metaphor on that. So we will use the maps to indicate what has been visited and the frequency of each character. And the steps for us to be able to create the sliding window technique for this problems are going to be as follows. Step 1. Actually, I will also put it up here. We need to find the substring of S that includes all the letters from T. So the steps for us to be able to solve this particular problem are going to be as follows. Step 1, we're going to initialize 2 pointers, left and right, at the beginning of string S. Step 2, we're going to initialize 2 frequency maps called frequency S and frequency T to store the count of the characters in S and T. And we're going to create a variable counter to keep track of the number of characters from T that are missing in the current window. And we are going to create variables min, length, and start index to track the minimum window length and the starting index of the minimum window substring, then add the frequency of characters from T to frequency T. And I understand this is a bit of a long problem, so what I'm going to do is just break this up. We have really 11 steps to be able to go over, so I'm going to write out step 1, step 2, step 3, and step 4 to help follow along and break up the whole type of problem. So step 1, we're going to create our frequency maps. So the way we do that, that's actually step 2. Step 1, we're going to create 2 pointers, left and right, at the beginning of the string S. So the way it's going to look, int left is equal to 0, int right is going to be equal to 0 to initialize. And then step 2, we're going to create 2 frequency maps to store frequency and the characters we visited. So we're going to call this unordered map character int and then frequency S, and then we will have the same for T. Then for step 3, we're going to create a variable counter to keep track of all the characters from T that are visited, so counter equals T.length. And then for step 4, we're going to create variables min, length, and start index to track the minimum window length and the starting index of the minimum window substring. So I know that's kind of a lot, so the way we're going to do this is int min length, and this is how we initialize our minimum length. Int start index equals 0. This is just how we created. And then what we will be doing for step 5 is that we will scan, and then this part is going to add the frequency. So I'm going to make this 4a. Then add the frequency of the characters from T to frequency T. The way it's going to be done is going to look like 4 character ch for T, and we're going to add the characters in the frequency of T. Then we will have to move over to step 5. which will be scanning through our array until, hang on, you know what? So I'm going to divide this up into two parts. So we will need to focus on our right pointer, and then we'll focus on our left pointer. And then return the substring in S from start index with the length of min length. So step 5, when we're focusing on the right pointer, is that we're going to scan through our array until the right pointer has reached the end of our string S. Then step 6, if the character current position at the right is present in T, we're going to decrement the count for frequency of T, and if the count becomes 0, we're going to decrement the counter until we have our output set in place where everything becomes 0, and we're going to have an edge case for step 8 later on for the left pointer. Is 0. That'll be for step 8. So for step 7, what we'll do then is then we're going to move the right pointer to the next position, and then we're going to move over to step 8. Focusing on the left pointer, while the counter is 0, all characters from T are found in the current window, and then we're going to update the min length and start index if the current window length is smaller. Then while we're inside of this while loop, if the character at the left is present in T, we're going to increment its count in frequency T, and if the count becomes positive, we're going to increment the counter. Step 10 is going to move the left pointer to the next position, and then for our output, this is entirely for step 11, the substring S from return the substring in S from start index and length of the min length. All right, so to be able to go and focus on the right pointer, so steps 5, 6, all right, here we go. We can scan through the array relative to our S length. And this will be, in fact, we are going to, all of this entirely will be inside of our while loop that we have. So 5, 6, 7, 8, 9, and 10, aside from 11, are going to all be inside of our while loop that we will create. So just going to try to get the structure right to be able to help you folks understand and see clearly how this logic will work. So for step 5, what we're going to be doing is that we're going to scan our right pointer, right, and it's going to be less than s dot length. Then step 10, we will do this. For step 6, if the frequency of T count relative to S right what we'll do is that we will, if the character's current position at the right is present in T, at the right pointer, decrement the count for the frequency of t. So the way it's going to look like is we're going to have frequency of t, s, right, and then decrement. Then if the frequency of t is going to have the s right, hang on, greater than or equal to 0. We're going to decrement our counter. Then remove the right pointer to the next position. In step 8, while the count is 0, no, the current counter is 0, so the way we do this is that we will have while counter is equal to 0, all the characters from T are found in the current window. If so, the way it's going to look like right minus left is less than the min length, and we're gonna update our min length right minus left and the start index to be the left. In step 9, if the character at the left position is present in T, so if frequency of T dot count S left, then we are going to increment frequency of T relative to S left, increment that. If the frequency of T S of left is greater than 0, we're going to increment, hang on, let's count in frequency T, and if the count becomes positive, not position. If the count becomes positive, okay. Sorry if there was some confusion over here. If the frequency of left is 0, then we're going to increment our counter. And for step 10, we're going to increment our left. Just make sure, okay. Yeah, so we have a bracket misplacement over here. No, this bracket should be for yep, there we go. And then finally for our output, which will be step 11, the way it's going to look, return the substring S from start index with the length of the min length. Should be over here. So step 11 is going to look like this. Return. Just going to put this over here for the sake of clarity. Return the min length, which is equal to int max empty string or the substring with start index relative to the min length. Okay. I'm just double check to see if it's all correct. Just gonna run this. Bit of a syntax error that we have. Didn't capitalize on this. I am sorry for the syntax errors that I'm getting. Alright, steps. No parentheses over here. No. No. Okay, it passes all the test cases, and again, I'm going to have this all in the comment section as well, so you folks can also follow along at the same time. So let me submit this, and actually let me clean this up so that way you folks can see the entire solution, and then I explain the space and time complexity as well. Again, all this will be in the comment section down below. All right. Come on. There we go. Okay, cool. There we got that. So this is what it should look like. Let me just double check. Okay, submit this. Okay, now to just give a rundown on space and time complexity for a following solution, since our space complexity is pretty efficient for this. The time complexity for a solution is going to be O of n, where n is the length of string s, and we traverse s with 2 pointers, and in the worst case scenario, we traverse the string twice. Well, meanwhile, the space complexity is O of m, where m is the number of distinct characters in t, and we use 2 frequency maps, frequency s and frequency t, to store the count of characters. In the worst case scenario, if t could have all distinct characters, we're going to lead O of m space complexity. So yes, this was minimum window substring. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we are going to be going over the Blind 75 in C++, and today we're working with implement trie. Now, before we get started for the entire thing, we're not necessarily working with the input, output, what data structure / algorithm to use, and then our output questions. What we are really focusing on is filling out the whole data structure for the trie and working out how to what to do with exactly all 3 functions to be able to replicate the trie. For whenever going the question, a trie, pronounces trie, or prefix tree, is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. And so I can, however, showcase a few things. Let me just get the comments inside for each part for our solution. So a trie, need to initialize the trie object, insert, and our insert function is supposed to insert the string word into the trie that we have, and the search is going to retrieve true if the string word is in the trie, if the word is in the trie, and then starts with is going to return true if there's a previously inserted string that has a prefix. So like we're asking ourselves,
is there something that starts with XYZ? Pretty straightforward over what to do, and so what I'll be doing is just going over the steps over what to do to be able to solve this problem, so that way you folks can be able to apply this on your own time. So actually, I'm going to go over to the very first part of what we need. So this part is going to be for step 1. We're actually going to create a trie node for the characters of a given string. One of the constraints, luckily, is that word and prefix consist only lowercase English letters, and there are 26 characters in the alphabet, the English alphabet. And so I'm going to showcase the steps of what we need to do. This entirely would be step 2. Yeah, step 3, step 4, and then step 5. So going about each one, and I'm going to put all the necessary steps that we need to help break down exactly how to solve this problem. So, focusing on exactly how to solve the following problem, what we need to do is that for our following steps, for step 1 entirely, A, B, C, D, E, is that we're going to create our trie node structure. That what we'll do is that first thing is that we will, actually I'm just going to put this all in Roman numeral for clarity. So first part, we're going to declare an array to hold children nodes. Next part, we're going to declare a Boolean variable to signify there is a word. Third, we're going to define the constructor for trie node. And then we're going to initialize all children nodes to null. And then we're going to initialize isWord to false to start things off. So the way we're going to go about step 1 is that we are going to create a class called trie node, which will be public, and then we'll have 1, 2, 3, 4, 5, and actually this is going to be important. So 4 and 5 are inside of a constructor. So the first part that we're going to have is that we're going to initialize all the characters, children to be 26. And then the next part is that we are going to initialize isWord. So this is how we create our constructor, where 4 and 5 are going to be inside of it, to determine exactly, hey, we accounted for the character and determining if there is a word. So 4 int I is going to be equal to 0. I is less than 26, and then I is incremented as a typical for loop, and then children I is going to equal null. Then we're setting isWord to false. You can do the same up here, putting isWord and set it to false. I'm just putting it in for the sake of clarity between, hey, we have this, and then we're also setting it to false as well. Just saying, hey, this is how we create our boolean, and then we can set it to false. Now for the next part that we will do is that we will now declare the root node of the trie and then initialize the root with a new trie node. So this part only contains 2 steps that we need to do. Lies the root of the trie node, and then set the root to be the new trie node. So the way we go about this is going to be looking like this, strangely enough. So I'm just going to move this up here for further clarity. And that trie node for our root. And then inside of the object, this will be for step 2. Step 1. Root is equal to new trie node to initialize. There we go. As such. Now, for step 3, we're going to work on our insert function. We will declare the node to be the root, scan every character from our given word. If the node for the following character has not been inserted, we return false. We put in a new trie node. Then we set the node to the next child node. Then declare that we have inserted a word in the trie structure. Step 1, 2, 3, 4, 5, the way it's going to look. It's going to look like this. Yeah, I'm just going to clean up all this as well. Three point 1, 2, 3.3, 3.4, 3.5. So for inserting, trie node, root, and then we're going to scan for character, word, and then we're going to have 3 and 4 on the inside, and then since we're determining if the character has been inserted, so if the node of the children character, this is how we just put up for each character, and then we'll have new child, new trie node, and then the way it's going to look, so we have node equal to node children for 4, C, A. Mind you, we're dealing with characters, so we have to format it this way, and then finally we're going to declare that isWord is going to be true. So we do that. Now we're going to search. What we'll do for our steps is that create a new instant. We will declare the node to be the root. Then we will scan every character from our given word whenever we call upon this function. And then if the character is not in the trie from our root, we return false for isWord. Then set the node to scan for the next character on word. Number step 5 in this. If we have reached the end of the word, we will return true. But overall, the isWord value. So the way it's going to look like for search, it's going to be for the following: 4.1, 4.2, 4.3, 4.5. The way it will look, we have try node equal to root to search. Then we are going to scan. All right, hang on, 4.5. So char preach word. We're checking to see if the character is on the inside. So if node for children C A, we will return false. Then 4.4, we'll have the node move on for the next one. So literally it'll be this. And finally we will return the value. Return node isWord and move along. And finally, with the starts with, what we will do is that you can get, okay, is that for one. What we will do is that we're going to do the same thing that we did before. We're going to scan for every character of the word. Given the fact that we're looking for a prefix. In mind inside the parameter. There we go, that's more like it. So we will scan every character from our given prefix. Then, if the character is not in the tree from our root, we return false. Since we're just focusing on the Boolean right here if it starts. And the reason why that we set isWord is that for the end, and this just indicates false given the fact that we have a Boolean right here. So just for further clarity. And for the fourth part, we will redeclare as up here and scan no. Then set the node to the next character onward. And finally, return true, assuming there is a prefix since we scanned for every single character. So similar to the other two volume functions at the top, we're just dealing with this. So, so we're going to do a 5.1. 5.2, 5.3, 5.4, 5.5. First part, try node root 524 character prefix. Have the 2 as required if the node A will return false. Otherwise, in this case, we'll just keep going onward while scanning for every single character. Node children C A and return true. Okay, let's just double check to see if we have everything already set in place. Yes, yes. We've already did that. Trie node is the root. We created our instance of trie node. We've created isword, onward. Okay, let's see. Let's double check. All right, there is a semicolon error. Don't forget that. And don't forget that. All right, passes all the test cases. Let's submit. All right, now just to give a rundown and breakdown over space and time complexity for the following solution is that our time complexity for both inserting and, well, we are going to have it for every single different following function. Let me just, I'm going to, there we go. Let me clean this up and then also showcase to you folks what the full program looks like. Okay, now, just to give a full breakdown on our space and time complexity for our following solution is that the time complexity for both inserting a word and performing a search overall is going to be O of M, where M is referring to the length of the word or prefix being inserted / searched. And our space complexity is going, for the whole trie, is going to be O of N, where N is the total number of nodes in the trie. In the worst case, if we insert lowercase English words only, we would need a maximum of 26 nodes for each level in the trie. And so, yes, this was implement a trie, or create a prefix tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to go over the line 75 in C++, and today we are working with the problem missing number. Now, before we get started, if you're following along at home, make sure that you, if you want to, feel free to write the questions accordingly. For whenever we are dealing with these types of questions, we always ask ourselves these 4 questions: what the input is going to be, what data structure / algorithm / technique to use, what to do with that, and finally what our output's going to be. So again, feel free to pause the video and take some time if you're following along. Now, breaking down the question, given an array nums containing n distinct numbers in the range of 0 to n, return the only number in the range that is missing from the array. So, pretty straightforward. We have an array of nums, and we have an output of 2. The reason being is that with our following nums, n equals 3, since there are 3 numbers, so all the numbers in the range 0 to 3, between the lowest point, 0, and all the way to the highest point, we are accounting for all the numbers, and we have to figure out exactly which number is missing from our sequence between 0 all the way to n. And we're going to be using bitwise manipulation for this technique. Bit manipulation. That is a freaking spell. Anyway, so just to discern between our input and output, we are given an array of nums. We need to return the missing number in the sequence that is between 0 and n. Right. Okay, so the following steps for us to be able to accomplish this bit manipulation is that we are going to use the XOR operation used for exclusivity. And the steps for us to accomplish this are going to be the following. Step 1, we will initialize a missing integer for the missing number we will return. Step 2, we will calculate the
or of all numbers from 0 to n, and we will scan through the array. While doing so, we will XOR the current number with the variable, and then for the third step inside of our for loop, or outside of it, we're going to calculate the XOR of all numbers in the given array. And while scanning each num, we will use XOR to update where the missing number is, since we found the range earlier between 0 to n. Finally, we will return our missing number. All right, just to give a breakdown, I'm just going to move this all up here for the sake of clarity. So to go over the steps, we got step 1, step 2, step 3, step 4. And to make this work, this is what we're going to do. Int missing number is going to be equal to 0. Then what we will do is that we're going to scan for a range. So int I is going to be 0. Well, I is less than or equal to nums.size. I is going to be incremented to find the range. This is for us to find the range. And then we're going to take our missing number over here. I'm going to use the XOR operator to update for each index, so we know that we have already visited. And then we're going to calculate XOR for our missing number. So we do this by doing a for each loop, int num in nums, and then we will have our missing number updated in the variable, and missing number for num. Finally, return our missing number. So it's a 4-step process. It's very self-explanatory, very simple to go through. So let me just run this. All right, passes all the test cases, and it works. So yes, just to give a breakdown on the space and time complexity for our following solution is that the time complexity for our solution is going to be O of n, where n is referring to the size of the input array that we have. So relative to the bigger the number we have, the chances are between 0 and the biggest number. That is why our solution's time complexity is O of n. Well, meanwhile, the space complexity is going to be O of 1, since we're not using a data structure to store anything. We only use a variable to store, in particular, what the missing number is. So yes, this was missing number in C++. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to go over the blind 75 in C++, and today we are working with number of 1 bits. Now before we get started, feel free to pause the video if necessary. For whenever we are going over these types of problems, we need to ask ourselves these 4 questions: what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So we're given the problem: write a function that takes a binary representation of an unsigned integer and returns the number of 1 bits it has, also known as Hamming weight. Okay, that's pretty straightforward. They also give us a couple notes and mention about Java, and then also more Java, but we're working with C++, so, well, it's pretty straightforward what they want us to do with the data. They want us to write a function that takes the binary representation of an unsigned integer. And there are symbols that we use pretty much for the technique that we will be doing called bit manipulation. and allows us to get the binary representation of our following for our following input, where it looks like we're given a int of 32, so we are given an unsigned integer, and we need to return the number of 1 bits it has. So, looking at this, we just need to scan through all of our integers that we're given for any, well, all the binaries with a given integer, and we return the number of 1s. So the steps for us to be able to go about this, and I will also have a visual at the same time to be able to understand more on what forms of bit manipulation to use, which would be the following. So what we are going to do for our steps are this. Step 1, we have a given unsigned integer. We will create a count to keep track of the 1s. Then what we're going to do is that while scanning through our unsigned integer, if n at the specified index, which is represented by and, equals 1, we're going to increase our count. And then we will right shift the unsigned integer by 1 bit to check for the rest of the bits. And finally, we will return our count. So, the steps for us to be able to go about this. Step 1, step 2, and then step 3. Let me just clean this up. Focusing on these steps that we have over here. So step 1, the way how it's going to work, we're going to first create a count. Int count is equal to 0. This is how we first initialize. And then for step 2, while scanning through our unsigned integer, so the way it's going to look like is that while n doesn't equal 0 specifically, since we have an unsigned integer, A and B, and we'll finally have C for step 3. If n, specifically for 1 at a given bit, equals 1, then we will increment our count, since we are returning the number of 1s. And then what we'll do is that, move B up here, then we're going to right shift, and this is how we right shift. There's also the option for left shift, but since we're not going in the reverse direction, we're only moving forward, we therefore use this signal for the right. And finally, we return the count. So let's just run this. All right, passes all the test cases. Let's submit. Okay, now just to give a breakdown on our space and time complexity for the following solution is that the time complexity of this solution is O of log n, where n is the given unsigned integer, and the while loop iterates for each bit in the integer, and while the log n, in which log n bits is the worst case. The bitwise and n right shifting takes constant time. And meanwhile, the space complexity for the solution is O1 because we are not using a data structure to be able to store any of the variables. We're just using a count to keep track of everything. So yes, this was a number of 1 bits. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye.